All right. Good morning and welcome to the first day of Beyond the Basics, the Potential Role of Advanced Nuclear in Alaska virtual workshop sponsored by the University of Alaska Fairbanks, Alaska Center for Energy and Power. I'm Gwen Holdman. I'm the Chief Scientist at the University of Alaska at Alaska Center for Energy and Power, and I'll be your MC for the next 2 days of this workshop. For those of you who don't know me, my background is in energy engineering and policy, and nuclear is one of the technology areas I have been tracking and working in since around 2009, when we were first asked by the Alaska State Legislature to explore its viability as an energy source for Alaska applications. So I'm pretty excited about the agenda we've been able to assemble here over the next couple of days. So just to give a little bit of background for those of you that may be new to this speaker series, this is the third in a series of 4 quarterly workshops in our Continuing Conversations virtual workshop series, where we take deeper dives into specific topics that are timely and important and leading up to the Alaska Sustainable Energy Conference, which is taking place for the 5th time this May. We kicked this series off back in August with lessons learned in transmission planning, followed by the business of Alaska rural energy in October. Our 4th and final workshop, which is going to take place in April 1st and 2nd, is on alternative fuels. If you missed any of the ones that already happened either this year or in previous years, and we've actually explored the topic of nuclear energy previously, they're all available online. I think that the team from Government Event Services is going to drop the link in the chat here. But each of these is designed to have these deeper conversations leading up to the 5th annual Alaska Sustainable Energy Conference, which will be held in person at the Dena'ina Civic and Conference Center in Anchorage, May 19th through the 21st. So we hope that many of you will be able to join us for that event as well. So when we asked for topic suggestions for these workshops, advanced nuclear rose pretty clearly to the top. It was the most requested topic. And so, this workshop, we view it as very much by popular request, and based on the number of registrants, which was the highest that we've ever had. And so far we've got a little bit over 130 participants today. It does look like this topic has a lot of interest. And it also comes at a pretty opportune moment. There's a lot happening on this front right now. And so I feel like it's a good time to take a step back, take stock, and get an update from a lot of the experts that we have in the various panels and enlisted as speakers for the event. I've been personally following this technology for about 16 years, and it's pretty striking to me, at least, how much momentum we've been starting to really see in the last, couple of years, with projects moving really from the drawing board into real world deployments. And so we'll be able to hear a little bit more about that. And we're going to hear just in general about a lot of those developments over the next couple of days. We have a really strong group of speakers, as I mentioned, people who are really working at the forefront of this industry and who have taken time out of their very busy schedules to be with us here today and tomorrow. I do want to note just right here at the beginning that we won't be able to cover every single aspect of this topic during the workshop. We've had to sort of really curate the conversation because we've only got 4 hours today and 4 hours tomorrow, and this is a pretty expansive topic with a lot of different aspects. And so ASEP is also planning to relaunch the Alaska Nuclear Energy Working Group. And I'm going to share a little bit more information about that later, but I just want to mention that as a way to continue this conversation about nuclear energy beyond this morning and tomorrow morning. And we're really hoping to continue to dip into topics that we're not going to be able to touch on over the course of the next couple of days. So I hope that many of you, regardless of what your perceptions are on nuclear or the value that it may play for Alaska's energy future, I hope that you sign up if you are interested in this topic. We're going to hold the first meeting on February 24th, and our plan is to focus on what we found through our polling is one of the biggest concerns or questions Alaskans have, which is looking at the fuel life cycle. What do we do with nuclear waste, and what is sort of the plan for for long-term disposal of high-level radioactive waste. And so that's going to be the topic for the first nuclear working group meeting. I actually visited Finland's Onkalo long-term repository for nuclear waste earlier today. I'm actually dialing in from Helsinki, and this is the first geologic storage site anywhere in the world for the long-term disposal of radioactive waste, and it's coming online this year. And so that's pretty exciting, and I'm looking forward to sharing a little bit about that, as well as hearing about the plan and the process in the United States as well. So bringing us back to today, on your screen, you'll be able to see the agenda for this morning. We're starting out with a couple of opening remarks before we launch into a bit of an overview on nuclear energy advances for resilient power solutions. This is kind of an opportunity to level us up and make sure that everyone is a little bit on the same page of what we're talking about when we talk about advanced nuclear energy. That's going to be followed by, a panel, Why Now? Nuclear Energy's Current Moment. So we'll bring a couple Alaskans together with folks from national labs and have a little bit of a dialogue. I'm really encouraging all of you to participate in terms of the Q&A by dropping questions into the chat so that we can make sure that we're getting those questions to the panelists and having a really robust conversation. That'll be followed by a short coffee break. And then we'll move into a 10:30 session on what's happening with the U.S. Department of the Army and why nuclear, followed by a discussion about the future of U.S. nuclear licensing, and then wrapping up with kind of hot off the press our polling results from doing our most recent version of a third statewide nuclear polling survey, and just kind of generally about energy polling questions to Alaskans. And so we'll be able to share that at the end of today. So just a quick preview of day 2. And you guys probably have seen a copy of all of this, but just to go over it really quickly. Again, just quick recap at 8:30 in the morning. I'm going to be your MC for day 2 as well. So at 8:45, we're going to hear from Idaho National Lab and from the National Reactor Innovation Center about what's happening there and some of the testing and programs that are planned there, followed by an update from Oklo, who was selected as the vendor for the Eielson microreactor project. Have another break, and then move into the economics of advanced reactor technologies. So that's another question that a lot of Alaskans have is what are the economics of these systems, and does it make sense in terms of our other energy alternatives? And then we're going to follow that up by a final panel consisting mostly of Alaskans talking about what it would take. So just basically synthesizing all the information we've learned here and what it might look like to incorporate nuclear into Alaska's energy future. And so that's it for day 2. We're going to start with a couple of poll questions. So if you guys don't mind, if you can humor us in terms of answering a few of these questions, you can just go ahead and scan that QR code on the screen here with your mobile device, or visit slido.com and enter the code 1904537 and tell us where you are joining us from this morning. I'm going to do that as well. All right. And it looks like we're just getting a screening example here of that. We normally have a bit of a map, but I guess they're just up here on top. Anchorage, Alaska in general, Fairbanks. I see Utqiagvik in the chat, Idaho Falls, Juneau, Palmer, and a whole bunch of other places around the country. And like I said, I saw an Oulu Finland, so I'm in Helsinki right now. We're 11 hours time zone different, so glad to see someone else in my time zone. Oh, it's unfortunate. Hopefully we'll be able to like maybe put these all on a map or at least get a more expansive list tomorrow, because it definitely, we've got some interesting locations that I'm seeing on the screen along with you guys. And I also encourage all of you to just introduce yourselves in the chat. We've got 144 people that are dialed into this workshop today as participants, plus a few folks in the presenter room here as well, or support. And so just introduce yourself, just to drop some information on who you are, who you're with, where you're joining us from today, and you know, what you're hoping to get out of this if you have that capacity to do so into the chat. All right, should we go on to our next poll question? All right, so this is just quickly, I'm curious, what image, when you first think of nuclear, comes to mind? Like just the immediate first thing that comes to mind, the first thing you think of. And this will just be a little bit of a word cloud that populates as we hear from all of you. Simpsons. I like that. All right. This is great. Power, large cooling towers. That's sort of the iconic image. I actually thought we'd see more on the nuclear navy or submarines here. Blue glow, Cherenkov radiation. I like that. China syndrome, the Simpsons. All right. This is great. It's a lot of like, now these ones in the middle here are the ones that are being repeated. So expensive. Yes, we need to talk about the economics. All right. Looks like clean, nearly no greenhouse gases. The radiation symbol. Sandia. Waste. Workforce. Pollution. Reactor and econics. All right. Pretty diverse. 1979. Is that a movie? What is 1979? Somebody will have to share with me what that represents. All right. Should we move on? Okay. So this is sort of a version of how confident do you feel, or what you're coming to this workshop in terms of your understanding of nuclear. So instead of just asking you how familiar you are with it, I'm curious how confident you are in explaining it to a non-expert. All right, looks like we have a pretty diverse audience here. I know the basics seems to be winning out. Okay, so we have some folks here that are not confident at all explaining advanced nuclear to a non-expert. So I'm glad that we have an expert to explain it to all of us this morning. So we're going to get to Mark here in a minute. I'll just let this go for another minute. Yeah, it's like pretty even between not at all. I can explain it at a high level and I can answer most questions. And then we have a few experts. So Mark, I assume that you're in the number 5 category there. Okay, well, we can let that keep going, and I just want to do a couple of housekeeping items. Let you guys you can continue to fill that out if you haven't yet. But thanks for participating in those polls. A couple housekeeping items. As I mentioned, introduce yourself in the chat. Just share your name and organization, and if there's something specific that you're hoping to learn today and tomorrow, that would just be great for me to sort of understand and make sure we get some of those questions out there. And during each panel or after each presentation, we've made space for audience Q&A. So my plan is, because there's too many people here, that we're not going to be asking you to unmute, but I'm going to curate those questions. So submit them as they come up. So otherwise, I'm going to start asking questions, and believe me, I can keep going. So, but I'm going to keep an eye in the chat for questions that you guys have for our speakers. So get those in there as quickly as you sort of think of them. And then make sure that you're submitting them in the chat box at your bottom of your screen that you guys are clearly using right now. And so that looks great. There's also like the button for, you basically want to be asking the questions of everybody. So use the everybody feature, the like little green drop or blue drop down arrow. But if you have any trouble and you need support from the event staff, you can also do that drop down menu and then just ask specifically. The support staff can help you out if you need anything there. Okay, so again, recordings of the virtual workshops are available online at the Alaska Sustainable Energy Conference website, and that will include this one probably in a week or two from now. But the other ones are already up there, so if you're interested in that. And with that, I would like to move on and introduce a quick intro video from the governor of the state of Alaska, Governor Mike Dunleavy. So let's play his intro video.
Thank you all for joining us today, and thank you to the Alaska Center for Energy and Power and the University of Alaska Fairbanks for convening this great workshop. This event is part of our Continuing the Conversation series, leading up to the next Alaska Sustainable Energy Conference, which will take place in Anchorage this May. I want to begin by welcoming our many participants joining from outside Alaska. We appreciate the time you've taken to be here and your willingness to engage directly with Alaskans who are asking serious, thoughtful questions about Alaska's energy future. Alaska's energy challenges are not theoretical. We face declining gas supplies, aging infrastructure, and some of the highest energy costs in the country, particularly in rural and remote communities. At the same time, we are serious about pursuing opportunities for economic growth and attracting new industries to the state. As governor, I've always supported an all-of-the-above approach to energy, and I believe nuclear can be an important part of Alaska's energy future. For decades, nuclear energy has been discussed as something always just over the horizon. Today, however, we are seeing real demonstration projects move forward in the United States and here in Alaska. Two examples are worth noting. First, the planned microreactor project at Eielson Air Force Base, which represents one of the most advanced deployment efforts currently underway. Second, an effort that has received less attention so far is the Department of Defense Janus program. Just 2 months ago, it identified Fort Wainwright as one of the 9 candidate sites for a future microreactor demonstration. Alaska's energy future will not be defined by single technology. It'll be shaped by informed choices, grounded analysis, and open dialogue. So I want to thank you for being part of this process. I look forward to the discussion, and I hope this workshop helps all of us better understand the options in front of us.
All right. Thank you, Governor Dunleavy. So now please join me in welcoming Mark Nutt to the virtual stage. Dr. Mark Nutt is Pacific Northwest National Lab, PNNL's Nuclear Program Director. where he oversees programmatic support for the Department of Energy Office of Nuclear Energy, the U.S. Nuclear Regulatory Commission, and commercial and international clients. A full bio for Mark and for all of our speakers is available in the materials that you received when you signed up for the workshop. I don't want to read the entire bio here and spend time on that right now. But what we have asked Mark to do is come here and give a bit of a broad overview of what comprises of advanced nuclear reactor, or nuclear energy in general, and what the overarching state of the technology is. So thank you for joining us this morning, Mark. I'm going to turn it over to you to share your slides.
Okay, so before I get started and watching the polls, I'll offer that for those who explain nuclear frequently, know it at a high level, or know it mostly well, you can either think about going to get a cup of coffee or critiquing me. For those that answered at the basics or not at all well, I'm hoping this presentation will help you understand a little bit better and help you level set for you having informed discussions regarding nuclear energy going forward. What I plan to do is kind of walk through quickly some of the federal action related to nuclear that's been going on over the last several years. If you look in the press and elsewhere, I'm sure you're seeing a lot of chatter on nuclear energy, but I'll kind of show what's been happening. I'll go through a brief overview of the reactor technologies, kind of overview of what the reactors are, talk about the evolution and safety that's been going on over the last several years, and then the benefits and some of the challenges that are being faced. And then I'll finish with a status of what's going on in the industry, just so you can see kind of across the country everything that's happening. Gotta get the space bar right. So first, just a little bit about us in the program that I steward at Pacific Northwest National Laboratory. Is we're all about facilitating and supporting maintaining operation of the existing fleet, continuing to look at design, licensing, safety analysis of both conventional and advanced reactors, as well as the infrastructure needed to support them, fuel cycle infrastructure, et cetera. And we're also about enabling recycling, storage, transportation, disposal of spent fuel. I saw Gwen talk about the session that's going to come up on the back end later, and I think that'll be a very interesting session for folks to attend and learn more about kind of the back end of that. So on the legislation side, the policy, legal, regulatory framework for nuclear energy has been established for quite a long time. People, working with the NRC, DOE, and others, and starting in about 2017, there started being legislation passed, and it was bipartisan legislation to try to remove some barriers, to enable some things to go a little bit quicker, to get rid of some existing boundaries that were in the way. First in 2017, the Nuclear Energy Innovation Capabilities Act, or NECA, really kind of opened the way to establish public-private partnerships at DOE labs, established the Nuclear Reactor Innovation Center, funded some advanced reactor licensing, really aimed at getting the private side better connected with the work has been and is being done at the national labs. Then you follow that with the Nuclear Energy Innovation Modernization Act in 2019, aimed at modernizing the NRC. Then came in 2021, the Infrastructure Investment and Jobs Act, established the Civil Nuclear Credit Program that kept a lot of the reactors afloat. We were seeing lots of shutdowns and early premature shutdowns in the teens that aimed to correct. It funded the Advanced Reactor Demonstration Program, which has made some very significant progress that I'll talk to later. And it started really funding for getting what's called high assay, low enriched uranium, the higher enriched uranium that's needed to fuel the advanced reactors that are out there today. Then came the Inflation Reduction Act in 2022, with significant tax incentives for nuclear energy for both existing and new plants. That's enabled and caused a lot more interest in the area. And last, the ADVANCE Act of 2024, which really focused at modernizing the NRC, updating mission, cost and fee reduction, aiming at workforce, et cetera. Then came this year, and the new Trump administration has issued 4 executive orders on May 23rd, to establish their priorities on nuclear energy. You can see them here, the deploy advanced nuclear reactor technologies for national security, deploy reactors for national security, have partnership with the private sector, promote our exports, and use it as to provide power for critical infrastructure and national security. This was also came out with the reform of the Nuclear Regulatory Commission, kind of building on a lot of the work that was done in the Advance Act and some of the prior laws that I just talked about, but really pushed harder to modernize the nuclear regulatory framework, realign the NRC's culture and personnel against their mission, as well as reform the whole agency. Then the one on the bottom right, the reinvigorating the nuclear industry base, recognize that, it's not just the reactors when you think nuclear. You've got to have, the whole supply chain, the fuel supply chain, material supply chain, components. So it really aimed at reinvigorating a lot of that by, first the fuel cycle, brought in reprocessing as part of the policy, aimed to set up ways to get fuels companies moving. It aimed to accelerate production, expand our workforce, and strengthen the supply chain across the board. And then last was the reform of the nuclear reactor testing at the Department of Energy. And it was really aimed at streamlining reactor testing that could then lead to NRC licensing and commercial deployment. Really hope to foster innovation. And it led to the launch of the pilot reactor program that DOE got started this year, with the aim of having reactors critical by July 4th of this year. 11 companies are moving forward to try to achieve that goal. So really, what's driving the consideration or even reconsideration of nuclear energy across the country? The big one's increased demand. We've seen flat demand across the United States for years, and with the oncoming of data centers and AI and onshoring of industry, they're seeing a very significant projections of increased demand and a need to be able to power those using resilient energy grids. We want the grid to be resilient. We want it to be able to keep operating in the face of all the challenges that it looks at. We've got to do load balancing with intermittent energy sources that have been deployed over the last several years. Wind, solar, and nuclear can provide a very good load balancing source, as well as providing firm, reliable generation, 24/7 power, almost 365 days a year to help on that intermittent side. As well as data centers are looking to operate in island mode, having their generations behind the meter just dedicated to the data center itself. And then others are looking at black start capability, really being able to come back up from an outage or a grid loss event to really came up. One that surprised me, I picked up on about a year or so ago, was actually just a saturation of renewables in certain states where they have a lot of wind and a lot of solar. They really can't get any more on, and they've got to do some of this load balancing and keep their grids resilient, or looking at potentially using nuclear, as well as carbon-free power laws in some states. And it's, kind of mixed across the country, who's got them and who doesn't. I come from the state of Washington, and we have some pretty strict carbon laws within the state that are affecting some of the decisions that are being made here and causing interest in nuclear power. So real quick, the science, and this is like nuclear engineering 0001. The basics of all of these, the old reactors, the new reactors, is fission. You essentially split the uranium atom or plutonium atom. You send off about, on average, 2.5 neutrons, and they go on to cause more fission. What you do is you put control rods or other things that can absorb about 1.5 of those neutrons on average, leaving 1 to go cause fission, and you get a sustained chain reaction of fission. The fission event releases energy, and that energy then is captured and dissipated for heat. The uranium or plutonium is contained in fuel elements. What you're seeing at the top left is a fuel rod for a light water reactor and a fuel assembly that would go into a pressurized water reactor. Essentially, these are uranium dioxide fuel pellets, a solid ceramic. So those that put Simpson up in the polls, it's not the green goo you see that Simpsons typically go. It's solid material inside a fuel rod, and that rod is sealed as part of the defense in depth. They're then put into fuel assemblies. Those assemblies are placed into the reactor core, and down at the bottom right or bottom left, they're used to generate steam. Basically the existing fleet of reactors now are they just boil water, convert steam, make a turbine, spin the generator, and make electricity. And you could take out that nuclear part on the left, put a coal boiler in there, and you basically got the same system. Some of the newer advanced reactor designs are following very similar heat removal and energy generation. Some are using a little bit different technologies to convert the heat of fission into electricity. What's the safety hinging on? One is reactivity control, so you can control that fission reaction. As I indicated, you've got, on average, one neutron going to cause another fission. If you insert a control rod or another poison, you slow that down and power can reduce. You can drop control rods in a reactor and shut that fission reaction down almost immediately. Then you have to remove the heat. And that's through kind of the system I showed you on the left. Take the heat out, keep the reactor cool, don't let the fuel overheat. And then last are multiple barriers or defense in depth. You've got the solid fuel, the fuel rod it's contained in, the containment, the reactor vessel itself, the containment around it, multiple barriers between kind of the public and the radioactive material that results after the fission process. So talk a little bit about the evolution of reactors. They've been around since the 50s. We started with generation 1 reactors that were kind of the early prototypes that were tested. Some of them demonstrated, some of them were on the grid. And then we moved on and choices made for what we call the generation 2 light water reactors that are really the commercial light water reactor designs that are deployed across the US and pretty much across the world. They were originally designed with a 40-year life. They're licensed. Several of them have been renewed for another 20 years, and a few and more are looking to be renewed for another 20 years on top of that. Then the industry moved to generation 3. Again, evolutionary design improvements on the generation 2, but none of those were deployed in the US. Those were aiming for a 60-year design. Some Gen 3 reactors were deployed worldwide, but again, none here. Then they moved to the generation 3 plus evolutionary reactors, another evolution on the generation 3. They relied on more simplified systems, passive safety, et cetera. They're large light water reactors like the 2 that were just deployed down in Vogtle. And then there's also small modular light water reactors. SMRs, one variety of SMRs. For example, those built by NuScale, being designed by NuScale, GE, Hitachi, and Holtec. Then we have the Gen 4 revolutionary reactors, and these are the very different than the water reactors. They use advanced fuels, innovative coolants. They can be of small modular reactors or microreactors. Examples are high temperature gas cooled reactors, sodium cooled fast reactors, molten salt reactors. So different coolants, different fuels, different designs. So the big question and the big movement is in the advanced reactors going from Gen 3 to Gen 3 plus and Gen 4 is relying more on inherent and passive safety features. The current fleet of reactors typically, safely operate and protect safety using a lot of active features. It requires external input to function. You need a valve to trip. You need a pump to turn on. You need something to actuate to push water through to provide coolant to protect the plant and operate the plant. Then on the inherent side, you rely on kind of the fundamental properties or design choices of the reactor. For example, you look to design to achieve shutdown by what's a negative power reactivity feedback, or it's felt self-limiting. One of the examples of this is in a sodium fast reactor, where if the reactor starts heating up, the structural and fuel materials expand, allowing more of the neutrons to leak out of the core and not cause fission, which kind of turns the power increase around. And you also rely on passive features, natural forces, property of materials, et cetera. As example here is natural circulation coolant. A lot of the designs out there today, are really using natural circulation rather than forced pumping or forced pumping to remove the heat. Both advanced light water and non-light water reactors are moving. What this allows is, by moving to inherent and passive safety features, you don't have to have as many pumps. You don't have to have as many valves. Your design gets simpler, and which makes operations easier. It makes it safer, and it reduces the size of the plant and reduces the cost of having to deploy it. So current generation, we have a very strong demonstrated nuclear safety within the United States. The reactors are operating well over a 90% capacity, which means they're almost running 24/7, 365 days a year, generating power. They have to refuel depending on the reactor design, either 18 months or 24 months. So essentially they run for 18 or 24 months, come down for 20 days, refuel the reactor, do the maintenance you need to do, bring it back up, and off it goes again. It leads to high reliability. It's emission-free or carbon-free, and a firm, secure power that's out there on the grid today, which is why so many people are interested in keeping the current fleet alive and even potentially doing power uprates on it. The existing fleet does take a lot of water. If you look, they're all by fairly large water sources. People have mentioned in the poll the large cooling towers that are out there to cool them down. The large, they're expensive. They're high investment costs. You basically got to stick build the entire thing from the beginning, and they're less agile. These machines were built to basically bring up to full power and run for 18 or 24 months, delivering power to the grid, and then shut down for the refueling. They do some power ramp downs here and there, but typically the fleet operates at very high power, the goal of just putting electrons out on the grid. So what's an advanced reactor? And I show this slide because, I tend to see that SMR is begun to come kind of common nomenclature for advanced reactors. And I just want to show that, the SMRs are just a variety of the types of advanced reactors that are out there. There can be large reactors that can be deployed that are advanced reactors, from the 300 megawatt to 1,000 megawatt scale. Vogtle 3 and 4 are advanced reactors, and they're large. Natrium's about a 300 megawatt reactor. It's large. The small modular reactors are kind of on the 20 to 300 megawatt scale per plant. The image up above is the new scale with the small modular reactors inside the building. X Energy is looking at small modular, Holtec, GE, a variety are looking at these small modular concepts. With the intent there is the reactors are factory built, for the most part, shipped out to the site and installed. And then at the low end, you got the microreactors, where here the whole reactor is intended to be built in the factory, brought out, delivered, and essentially plugged in and turned on and operated. And then some of the business models at the end of the day, you're going to pick it up once it's done and take it away, maybe replace it with another one. These are on about the 1 to 20 megawatt scale. But all of these are advanced reactors. So, when you hear the word SMR, just kind of think about where it fits in this, and understand that there's a range. So some of the examples: advanced Gen 3 advanced light water reactors, the Vogels 3 and 4, NuScale's reactor, GE Hitachi's boiling water reactor, as well as Holtec's SMR 160 that they're looking to build. Then you go to what are the Gen 4 reactors, and a lot of these are being done under Advanced Reactor Demonstration Program that the Department of Energy launched several years ago. The two that are at the demonstration level are the Natrium reactor being developed by TerraPower, a sodium-cooled fast reactor, and then they're actually using a molten salt energy storage system to put some of the excess heat or excess energy they generate, when the power is not needed from the reactor. That allows them to run the reactor essentially full power, and then allows some peaking if needed on the grid. X Energy's XE100 gas-cooled reactor that's looking to be deployed in Texas. A high-temperature gas-cooled reactor, about 70 megawatts per module. Again, an example of an SMR on the right and kind of a larger reactor on the left. Also part of DOE's Advanced Reactor Demonstration Program are some kind of followers to those in a risk reduction category. All of these are Gen 4 advanced reactors, except the Holtec SMR 160 that's about at the right, the middle. They're all examples of Kairos's fluoride salt-cooled reactor, TRISO-fueled, Westinghouse's, just a wide variety. And then even below that, there's some other concepts that are still coming along a little bit behind even the risk reduction, still being developed towards eventual deployment. The idea with this is, Natrium and X Energy deploy, perhaps Kairos, Avinci, they'll be right behind them coming down the pipe to try their deployments and demonstrations. So what are the challenges of new nuclear? One that's talked about all the time is capital cost and financing. How much is one of these things going to cost to deploy? How are we going to finance them? What's the uncertainty? What's the risks? And people are trying to get their arms around that. Another one's what they call capacity accreditation. It's when utilities and operators have to do resource adequacy. They have to estimates, and they're going to put nuclear in it. They have to say, okay, what is the capacity of this asset we're going to deploy as part of our projections? And with some of these new advanced reactors, there's really no operating experience for them to go on. So there's a lot of uncertainty in what they predict, as well as predicting the cost modeling over their 60 to 100-year lifespans. What's it really going to cost to operate one of these things? Again, some of this is trying to, with the Advanced Reactor Demonstration Program that DOE is doing in these demonstrations, we'll get some initial information on a lot of this. One thing with utility resource plans, they really favor what's commercially available today in their estimates and studies, not kind of what's foreseeable in the future. We've also seen a dearth in to be able to construct large thermal generation within the United States. They did it for Vogtle 3 and 4, had to pull a lot together to get that to happen. Hopefully can leverage on the learnings down there and be able to get that workforce back. Supply chain in general, in particular fuel, namely uranium fuel supply, enriched uranium fuel supply, and be able to do it domestically has been a challenge, as well as people's public education and perception of nuclear. And, it's events like this that you're all attending that I think are valuable so that people have an understanding and education and about, whether the information that's being provided and how that affects decision making. So what's some of the benefits of the smaller size Gen 4? Well, they're modular. So you don't have to build the entire power plant to start generating power. I can deploy, say one, 70 megawatt small modular reactor, get it up and running and still bring online the other 3 or 4, depending on how big I'm going to build the plant. It allows some flexibility. Factory built components, rather than building everything, on site with the large reactor, you can do some factory builds. They're scalable. I could, depending on the power needs, you could deploy, 4 SMRs, you could deploy 6, you could deploy 12 in multiple unit stations if necessary. A lot of them are underground construction, below grade to deal with some of the seismic and other issues. They're typically smaller footprint, 20 to 80 acres versus 1,000. And they have smaller exclusion zones by how the reactor is designed and, kind of the hazards and events of an accident, quarter-mile exclusion zone, but as compared to some of the older ones having 10 to 50 miles. Affects planning, affects, overall cost of deployment quite a bit. They're flexible. They're designed to operate in a variety of different ways. They can load follow either the reactors and or the whole plants. They have improved ramp rates compared to the existing reactors. They can go up and down quicker, without, causing undue impacts on the fuel. They can do black starts. They can operate in island mode. They have shorter refueling cycles. In fact, some of the designs have really no refueling cycle. They will do online refueling, less water usage, kind of all of this. A lot of that just leads to more siting options for, the new Gen 4 designs as compared to some of the older Gen 3 designs. On the fuel side, the Gen 4s use higher enrichment and higher utilization fuel. You probably may have heard the term HALEU tossed around quite a bit. The typical reactors today operate on a 5% enriched uranium. The Gen 4 machines mostly all will operate on about 19.5% enriched uranium. And as part of the fuel supply we have to build in the United States to be able to generate that. And the Department of Energy is putting a lot of investment and working with the private sector to build that. Some of the fuels, self-contained non-meltable fuel, the TRISO fuel that's out there that's been, designed and is being qualified. And again, shorter or online refueling. Again, that's going to help drive the capacity factor of the reactor up. The coolants are all improved efficiency. They operate at higher temperatures. They have simpler containments because of the use of inherent and passive safety features. They can operate at lower pressures than the existing fleet. The coolants are less reactive and corrosive to the structural material. And kind of this leads to having to have fewer redundant and backup cooling systems. Really, again, it allows for a more simpler, cost-effective, easier to operate design. So what's going on in the current fleet? And what this chart on the right or the left shows is, from the NRC, these are the years the current fleet's licenses extend, and it's dated, about 2025. So it's a bit old. Things have happened. So what we're trying to do, or what the industry is trying to do, is really pull this to the right. If we wouldn't do anything, our current fleet would have shut down in about the mid-2050s under the licenses they had. So with a lot of the tax credits that were provided by the laws I talked about earlier, the Advance Act and other, NECA, NEMA, and others, it's allowing the industry to make the decision that we can keep these plants afloat. Again, back in the teens, the late 2000s into the teens, a lot of the reactors were shutting down and decommissioning, just based primarily on economic decisions. And that has changed. So now we're seeing a lot of companies that have got one license renewal to operate for another 20 years are coming in for subsequent license renewal to basically run the reactor out to 80. The list at the top right shows all those that have completed NRC subsequent license renewal. There's a handful that are under review right now. We potentially got Vogtle 3 and 4 online in the last few years. And we're looking at restarts of reactors that were shut down, primarily based on those economic reasons, and things have changed now. They're looking at bringing up Palisades in Michigan, the Crane Clean Energy Center, which was formerly 3 Mile Island 1. And I think that was the 1979 comment that Gwen asked about. I believe that was TMI 2. And then Duane Arnold in Iowa was going to come back up. So they're now seeing these much more as assets and, going to invest back in them. And there's even talking power uprates to these machines to even get more power out of the fleet that's already out there. And this chart, I'm not going to go through it all. It's probably an eye chart, but if you look through this and count, if I counted correctly, there's future submittals and applications for subsequent license renewals from 27 reactors coming over the next few years. So it's going to get busy over the next 5 years. The Nuclear Regulatory Commission is going to have a lot of these on their plates, and will really test their the reformations and things that they're trying to put in place to be more efficient. And if you look at the advanced nuclear projects underway, a handful of stuff's going on. TerraPower and Pacific Core are looking at their sodium-cooled Natrium reactor in Wyoming at a retired coal plant. That construction permit's in review with the Nuclear Regulatory Commission, and it's getting pretty close to being done, and decision will be made. X Energy and Dow Chemical are pursuing a reactor in Texas, and that'll be used both for power and provide industrial process heat for the Dow plants. GE Hitachi and Tennessee Valley are looking at a BWRX 300. That's a Gen 3 plus SMR at the Clinch River site in Tennessee. They've got their construction permit in with the NRC. And GE is also working up in Ontario with Ontario Power Generation. They did receive a construction of the first of their three BWRX 300 at the Darlington site in Canada. So they're building one right now. Kairos is a triso-fueled molten salt cooled reactor. They have received construction permits for 2 test reactors, the Hermes and Hermes 2 reactors that they're deploying at Oak Ridge. Fermi America, a company in Texas, has tendered 2 parts of their combined license application for the Fermi America President Donald Trump Advanced Energy Intelligence Campus. They're looking at Westinghouse AP1000s, large Gen 3 plus reactors, the same that were deployed in Vogtle. Holtec's pursuing an SMR 300 at Palisades. There's power agreements between developers and hyperscalers, Meta, Google, Switch. And then last, we got a company, Entra One, that's got a collaborative agreement with Tennessee Valley Authority, looking to deploy 6 gigawatts of NuScale Gen 3 SMR technology within the Tennessee Valley Authority's area. So a lot is going on. It's really moving ahead. It looks like this renaissance may be real, and we'll just have to see how things progress. More is coming. You can kind of see all of these companies are in some engagement with the Nuclear Regulatory Commission on or have notified them that they intend to engage. So there's a lot of developers out there with a lot of different reactor designs that are aiming to engage with NRC and start advancing their technologies towards deployment. So just in closing, there's a lot of information out there you can get. I pointed to 5 areas for resource here. DOE Office of Nuclear Energy, Nuclear Regulatory Commission, Electric Power Research Institute, Nuclear Energy Institute, and the Gateway for Accelerated Innovation in Nuclear that's operated out of Idaho National Lab. So there's plenty of information out there where you can go out and get and learn more. And with that, I thank you for your time. And Gwen, I will give up the screen and go back to you. You're muted, Gwen. I can't hear you.
Can you hear me now?
Yes.
Okay. I guess I can, I have to use my headset. Okay. Well, I hope that you can stick around and join us for this panel we have coming up. So thank you very much for your introduction. And we're running a few minutes behind, so I want to quickly bring our panelists to the stage to join Mark for a little bit of Q&A, and hopefully the audience is dropping some good questions in here. I'm going to start with Neil. I see that you've been on here for a while, so thanks for listening in here. Neil is with the state of Alaska, Alaska Department of Environmental Conservation, DEC. Alaska DEC is the leading state agency for nuclear-related activities, and recently Neil took the lead. Well, the DEC took the lead in updating state regulations related to nuclear microreactors. So I wanted to make sure we find some space for DEC in the agenda here. Lou Florence is the president and CEO of Doyon Utilities, a Fairbanks-based utility company that provides energy, water, and wastewater services to the three of the major Alaska military installations. Lou is a pretty familiar figure in the Alaska energy space, but what folks are not necessarily familiar with is that he has held a senior nuclear reactor operator's license. So he's one of the few Alaskans that have some real practical experience in this field, and he's served in the Navy on board the USS Baton Rouge as a reactant operator. So thank you, Lou. And then finally, Richard Griffith is a senior manager of nuclear energy safety and security at Sandia National Lab. We're pretty lucky to have a lot of the different labs that are working on different aspects of nuclear energy joining us for this workshop. So we really appreciate Richard's time as well. They all have a slightly different mission when it comes to nuclear technologies. So again, their full bios are available in the materials that you have ahead of time, but just in the interest of saving time, I want to keep the intro short. I'm going to ask each of you to just give a little bit of a quick overview that we've discussed in advance. And let me see, I am thinking, who did we agree that we were going to start with? Is it Lou? Did we say we were going to start with you? Yes, you're raising your hand. Okay. All right. I'm going to turn it over to you, Lou.
Great. Thank you very much, Gwen. Thank you for the introduction. Good morning, everybody. Great to see a big crowd of people. So I'm going to talk for just 5 minutes, no more, to share a little bit of a utilities perspective on nuclear in general and how we think about it specifically in Alaska. So Gwen gave you a little bit of my background. It's fair to say I have a view on nuclear power, and frankly, it's a very favorable one. But as a utility executive in my current role, I'm part of the decision-making process on how to meet our customers' energy needs. And so those are always difficult decisions. Because they involve high capital costs, long-term assets. So it becomes very important to get these decisions right. And as one of the options for energy supply, nuclear is inherently attractive for a number of reasons. It's baseload energy, so intermittency is not an issue. If the advanced reactors prove to be as reliable as the existing designs, then we know that they can operate with very high capacity factors. Nuclear plants provide energy security. You don't have to worry about when the next barge of fuel is coming. So they go for long periods without refueling. So it's attractive. But that all being said, when I look at possible nuclear options, I really think about three things from a utility perspective. First is safety. Second is stakeholder buy-in. And third is cost. It's fun to talk about the technology, but when it comes down to the decision, these are the things that we have to think about. So safety's first. And Mark talked a bit about this, but the safety has to be demonstratable for every aspect of the plant's operation and the plant's life cycle. Transportation, handling the fuel, operating the reactor, disposing of the spent fuel, remediating the site. That's all got to be considered. It's all got to be very explicitly discussed. So the good news here is that while we haven't been building very many new plants, designs have continued to improve over the decades. And so we've got improvements in fuel design. We've got improvements in safety system design. What I tell people is that these are not your grandfather's reactors. Extensive use of fuels, advanced fuels, and passive safety systems really reduces the risk of radioactive release from advanced reactors. Like in the case of the microreactors, the designs are essentially walk-away safe. There's essentially no chance of a meltdown, even after a sustained loss of power. So these are important factors to consider because people will actually ask about them. They want to hear about it, which brings me to consideration number 2, and that's stakeholder buy-in. So when you ask about nuclear power, very few people talk about the remarkable safety record of the nuclear plants that have provided 20% of the United States electrical demand over decades. What do they mention? They talk about Fukushima. They talk about Chernobyl. They talk about 3 Mile Island. They ask about radioactive waste disposal. Here in Alaska, they talk about Galena. They talk about Fort Greely. They talk about Project Chariot. People need to be heard about these things, and they need information that they can believe, trust. There has to be a simple, solid story about safety that can be put out to everybody. There has to be a concerted effort on the part of anybody who plans to deploy a nuclear plant. There has to be a concerted effort to engage, to listen, and to educate stakeholders. This is just, it can't be overstated. This is paramount. Even with that, though, cost is still key to the decision of whether to use nuclear power. And this is the third consideration. The life cycle cost has to be competitive with other forms of baseload generation. And speaking specifically about Alaska, you can really reduce us to two broad use cases. First, there's the Alaska Railbelt grid that goes roughly from Anchorage to Fairbanks down to Delta Junction. And then there's everything else in Alaska. It's difficult to see without either direct grants or subsidies how either a small modular reactor or a microreactor makes sense economically on the rail belt today. The exception of that is at our military installations, where other considerations besides cost might be the most important. But outside of the rail belt, many locations pay extremely high costs for energy. So the opposite is actually true. It appears that microreactors would be competitive today if the safety is there, and I'm confident that it will be, and the buy-in is there, which I think is a challenge but achievable. There's a role for microreactors here in Alaska as soon as they become available. That's it. Thanks, Gwen. Back to you.
Great. Thank you. Thank you, Lou. Neil, do you want to go ahead and go next?
Sure. Yeah. So, yeah, I'm Neil Leonard. I'm with the DEC Solid Waste Program. I'm also the Alaska representative for the Northwest Interstate Compact for Low-Level Radioactive Waste Disposal, compact of 8 states for low-level disposal of radioactive waste at Richland facility. So, kind of a summary of how DEC is involved with these things is we were tasked with actually proposing regulations back in 2022, 2023. And the purpose was to provide nuclear facility siting requirements and also identify the permitting process. And the scope was to include that permitting process and also identify local approval process, because it was also identified in the statute, and then also location requirements. It allowed us to provide an environmental review and also promote the local involvement portion, which was, like Lou was mentioning, buy-in from the local entities is absolutely necessary and crucial, and that's a part of statute. And so our regulations do not cover any aspect of radioactive or nuclear safety. That's all managed through NRC licensing process. But our regulations that we wrote apply to 5 different types of facilities, one being microreactors. This was prompted in 2022. Legislature passed a bill which amended the current statute to basically streamline the state permitting process for microreactors in lieu of lots of support. And then one change that had to happen, though, in that 2022 statute was actually to the original statute required that the land could only be constructed on land that had been designed by the legislature to be used as a site for siting a nuclear reactor. So that was actually changed. And what it did is it basically still required the municipal approval as well as a permit through DEC. So that part still was required, but it was based on the siting requirements. Once again, nothing to do with radioactive safety or nuclear safety. And so, in short, there were numerous things that took place that happened. This legislative bill that changed it, and also there's a lot of microreactor projects being proposed in Alaska, and so it prompted our program to actually take the lead in developing these regulations to accommodate these projects for the statute that had been in place for years, but it was changed in 2022. We we have to the main thing that our regulations we had to ensure was included as part of the statute change was to include the local government approval process. So we as the state, we can't issue a siting permit unless we have jurisdiction or local municipal approval. Now, for example, if we're not actually located within if it's part of an unorganized borough in Alaska, it actually requires the legislature to approve that siting location. So that portion has been incorporated into our regulations. They took effect in actually August of 2023. It was a really quick process, a lot of work put by lots of different folks in our program to really get these things done. And so we're ready. Once we receive an application, we'll initiate that process. So, and just a real quick thing on our location requirements. Our location requirements are based on different setbacks, based on different like power utility regulations, those types of things. Once again, it was not on nuclear safety or radioactive safety. It was more on the environmental component of the other factors associated with an operation of one of these types of facilities. So, yeah. With that, that's my brief introduction of where the state is as far as our involvement in these types of projects.
Thank you, Neil. I appreciate it. Richard, can I turn it over to you?
You sure can. And like Neil and Lou, I had slides, but I think I'm just going to talk a little bit, introduce myself, and talk a little bit about some of the things that we've been working on and thinking on to enable, if there's questions or parts of the discussion, maybe to tickle some thoughts about things to ask about. So first, to introduce myself, I'm Richard Griffith. I lead Sandia National Laboratories Nuclear Energy Safety, Security, and Innovation Program. Sandia National Labs is one of the DOE national laboratories. We're actually one of the 3 national security laboratories that work under the NNSA. And our role in energy has actually been growing for 50 or 60 years, ever since the oil embargo in the early 70s. And so Sandia as a laboratory has been working in all forms of energy for many decades through the lens of national security. And, energy security, national security is energy security. So without energy, we really don't have a secure nation. So that's sort of the lens that we as a national security laboratory have come to the energy domain. We actually started working in nuclear energy in the mid 70s to support what was created to be the Nuclear Regulatory Commission. And so one of the key roles that we as a national laboratory play is providing impartial scientific and technical advice to government agencies. And in that role, we partnered with the newly formed NRC to help provide that kind of independent scientific and technical capability. Over those many, many decades, we've developed all kinds of analysis capabilities, areas of expertise, all to support the NRC's regulatory mission. So when the NRC receives a license application from a company that would like to build and operate a nuclear reactor, there's a big, long licensing and permitting process. Some of the speakers have alluded to that. So the Nuclear Regulatory Commission, as a federal agency, has a responsibility to evaluate that license application and ensure the protection of public safety. And so to do that, they need scientific and technical capabilities to sort of understand how these reactors operate, to understand the safety of these reactors, to help make decisions about siting the reactor and if there's appropriate sort of emergency response plans in place. All kinds of issues have to be addressed as part of that licensing process. So I think it's one thing I would say is, as Mark teed up very nicely, our regulatory authorities, the regulatory agencies within the United States that are sort of supporting what we hope will be this new nuclear renaissance have expanded from the NRC only to the DOE and to the Department of War. And so all of those regulatory agencies are needing and using the kinds of capabilities to evaluate sort of these systems to decide whether or not to permit and license them. The point I'd like to raise, and it sort of nicely complements the awesome overview that Mark gave, is to also think about what's changing in the nuclear industry. One of the things that Mark alluded to was the current generation of light water reactor plants are constructed. And so if you've ever seen movies or videos of how these giant light water reactors have built, it's a huge multi-year construction project. And they're all sort of built on site. And after they're built, then they're inspected and licensed and begin operation. This new generation of microreactors and SMRs, in particular microreactors, are shifting the paradigm more to the idea of producing those reactors. So they will be built in a factory. And after they're built in the factory, they'll be shipped to the point of use. So you can start to think about them, more as we would think about cars. I mean, they're very complicated engineered systems, but they'll be built in a factory and assembled and shipped to the point of use. Sometimes they'll be fueled at the factory. Sometimes the fuel will travel separately and they'll be fueled on the site where they're going to begin operation. But this is a very different approach to nuclear energy, and it has required a lot of different thinking about how we will ensure the safety and security of those systems. And so I just want to draw everyone's attention to the fact that because this is a very different idea, part of what Sandia does and what the regulatory agencies are doing, sort of looking at that whole life cycle, right? So the factories that are going to produce these reactors, if they are going to fuel the reactors there's safety and security questions that have to be answered about those production facilities. If those reactors are shipped then across the country, say up to Alaska, they have to travel on roads if they're being shipped by trucks or rail. And so there's this whole life cycle of the journey of these systems to the point of use. And it's more than just the reactor. And I guess that's where I draw the audience's attention to. It's everything that has to happen around that reactor to enable it to be a useful part of some system. So I mentioned the production, the transportation. There's the questions of where you site it. So then you site it. It has to be connected into an electric grid or a microgrid. So it has to be integrated into the infrastructure where it's going to provide that electricity. All the people around that, this question of siting, community engagement, emergency response services. So anytime anyone builds anything, the local fire department and emergency response community have to be part of that process and thinking about what that might change about how they prepare or how they train their first responders. When that reactor is operating, we all hope and believe that these passively safe systems are going to be much safer by design. But there's still questions of safety and security of these systems and how we're going to sort of protect them and manage them and operate them and provide a level of security for them. And then we have what we call the back end questions. When the reactors are ready to be refueled, or in some of these concepts, the whole reactor would be returned to the factory for refurbishment and refueling. So these are all issues that are sort of different from the current nuclear industry. And these are all kinds of interesting questions and opportunities and things that have to be addressed for this nuclear renaissance to really take off and to have nuclear energy become a larger and larger part of the nation's energy supply. So these are some of the many, many, many issues that we and other national labs are working and trying to support, again, our federal agencies as they consider and adopting these technologies and then driving them out into use. Okay, so I'll stop there, and that's sort of where I spend all my thought cycles and all my effort.
Yeah. Thanks, Richard. I'm actually going to start with you for the questions, if you don't mind. I'm
I saw I
actually
tickled your interest there, so go
Yes,
ahead.
exactly, exactly. Well, you kind of, definitely discussed a little bit broadly, like sort of the process or the framework for licensing, or how we're thinking about these new reactors. I think there's a curiosity or a question from Alaskans, is like, how do we think about really the specific licensing process? Like, maybe you can talk a little bit about the Part 52 framework, and really looking at the site versus like the particular technology, making sure that those are matched up. And in particular, there's interest in, we have a lot of natural disasters in Alaska.
Mhm.
Where in other parts of the state are very earthquake prone, others are pretty geologically stable. We have flooding events. There's a lot of
Yeah.
different hazards, forest fires. So how is that kind of taken into account as part of the site licensing process?
Yeah, those are great questions, and I will draw everyone's attention to, we do have a speaker from NEI a
Yes.
little later in the workshop, that's going to talk in a lot of detail about that licensing and regulatory process, and in particular how things are changing. And I would say again, in Mark's slides, he sort of highlighted this series, we call it the Big Four. There's four
Mhm.
big executive orders that the administration put out that are really sort of dramatically reshaping the nuclear energy in this country, and changing both the way that the regulators operate and the way that our Department of War thinks about and is driving to adopt nuclear energy, and also the Department of Energy. So the landscape is really shifting. And so I want to be really careful to highlight things have been, the regulatory approach and processes for nuclear energy have been evolving over time. But I mean, we've had the NRC in place since the mid 70s. So we have a set of processes and approaches to licensing and operating and regulating nuclear reactors that have been up and in place for a very long time. Things are really changing very quickly. And I think both the Nuclear Regulatory Commission and these newly constituted authorities for the Department of War and the Department of Energy to have sort of independent licensing authorities over nuclear reactors is frankly something that's still getting sorted out. So to answer your specific question, I mean, in general, the decision to allow a nuclear reactor to be built and begin operation it's intimately tied to the question of siting. And so when a site selection process is underway, that's a big part of the case that a utility or a vendor is trying to make to the NRC in terms of actually getting a construction permit and eventually an operating permit. Um, we have to look at the risks associated with that site. Perfect example, right? If you're trying to build a nuclear reactor on a fault line in California, probably the NRC is going to say no, right? So there's a very, very extensive scientific process based on existing data, based on historical data, based on geological site reviews, based on evaluations of floodplains, extreme weather events, because to ensure that a nuclear power plant can be built and operated safely, you need to look at all of these things, and you need to assure yourself and the public, which I think the NRC would strongly endorse as a key part of their mission, assure everybody that all these factors have been looked at, and that when the nation grants an operating permit for a reactor, that they have looked at everything and assured that, look, it's not sitting in the tide zone and will be underwater shortly, or that an earthquake is likely to happen in a way that would disrupt plant operations. So again, all of these things are looked at through probabilities. And so very geologically stable areas are obviously preferred sites. Sites that do not have flooding or extreme weather events are preferred sites. So whatever locations are chosen, that's the sort of screening process that everyone has to go through. And certainly that vendors, utilities have to go through, again, to have a credible license application to the NRC. It's a complicated process, and that's why I wanted to highlight it's not as simple as, hey, let's just throw that reactor over there, park it up against that that shed, and run an extension cord to it. It's a very detailed, thoughtful process to get approval to build and license one. I hope that's helpful. Does that
Yeah,
answer
no,
your
that's
question?
That's great. Yeah, thank you. And made a note to myself to make sure that we also include that in our questions for Spencer when he gets a chance to talk to us a little bit
Oh,
about.
I'm totally
Yeah.
going to help grill him because
Yes.
it's an evolving topic. There's no really hard answers because we're all sort of figuring it out. So I really look
Yes.
forward to hearing his perspectives about this.
Good. Yeah, no, I agree. And you kind of alluded to, what Mark shared earlier about these executive orders from last July. And I'm kind of curious, and I guess, Neil, I might bring you in here too, but I'm going to ask Mark to talk about this first. Governor Dunleavy, as Neil kind of talked about, advanced this legislation a couple of years ago that created this new category for reactors under 50 megawatts and sort of streamlined in-state approvals. I'm kind of curious, like from your perspective with this evolving sort of environment that we're in from like a licensing standpoint and just writ large, what else could states be doing right now to sort of be ready for this technology as it starts to mature? Like, are there areas where states really have leverage that we should be focusing? What are your thoughts on that?
I'm thinking, I'm like Richard, most of my effort supporting the federal agencies and developers.
All right.
It's an interesting question. I mean, Iowa's launched a task force to look at it for their state themselves, and
Right.
I'm chairing that task force. And to me, a lot of if you look at what's been done nationwide, there's a lot of states that have done these feasibility assessments. So, there's a lot of them that are written up, here's what they know about the technology, here's what they know about the cost, here's what they know. It does become down to, state questions, are there legislation? And, I don't know Alaska well enough to be able to say, you should look at this versus this.
Sure. Yeah.
I think you're doing the right thing here of trying to get as many people aware and understanding the technology and knowing what the questions are and the issues on the table, which I think is phenomenal. But yeah, I don't know if I'm real comfortable on opining on what the state should do.
I might pass that off to Neil or Lou. Or Richard, do you want to chime in there as well? Do you have any
No,
thoughts?
I want to hear what Lou has to say because
Okay.
this has been a big part of his life. So I'm curious.
Yeah. If you had a magic wand, Lou, is there anything at the state level that we could be doing?
The reason I pause is that I think especially here in Alaska, the states kind of laid out the red carpet. They've done what they needed to do, right? The governor and the legislature saw what was coming. They enacted the legislation. The regulatory branch kind of took a hold of it and said, we're ready. And then we're all looking back at Washington D.C. again, right? So I think that the state's done a good job here. As we go along, I'm sure that there's more engagement and more that the state will be involved with. But I think this is really when do we get nuclear reactors are difficult to design. They're difficult to build. But the reality is they're pretty easy to operate, and the state's role is going to be primarily in that operation. If we can get through the actual, how do you build it? How do you get it up here? How are we going to manage it? How are we going to site it? How are we going to permit it? All the hurdles that Richard referred to. The operators in the state are going to kind of join hands and go down the road together. It's going to be, I don't want to say it'll be easy, but it'll be simpler than the front end work, I think.
Neil, do you have anything to add?
Yeah, no, I mean, I think, we were given this direction, just like everyone had mentioned. I think, that was the first part from our perspective as far as an actual siting permit goes. We developed these regulations to accommodate this streamlining process so that our component is laid out for anyone interested in pursuing this. And I think the stakeholder Lud mentioned this. Everyone's mentioned this. Getting everyone aware of it, and the municipality buy off. That's going to be something that that was in statute. That's in statute. So that's something that we had to incorporate into our permitting permitting or siting regulations. And so that process, I think, will evolve. It'll be interesting to see how that process moves forward and how that decision-making process is made by the local municipality, or in the unorganized borough, it goes back to the legislature. So there's more to come on that, but I think as this moves forward, the process has become more and more defined. And once again, our portions aren't with the new radioactive safety or anything. Ours are for those other sources. And so, in some of the questions as far as some of the concerns with disaster prone areas, coastal areas, we did incorporate those into our siting locations, requirements. We do have a number of setbacks that are required, based on some of those things that we've talked about. Some of those are based on power utilities in different states. Some of those are based on different types of facilities, regulatory setbacks. And so we did try to incorporate some of those things into our siting requirements, not necessarily on the nuclear safety portion, but in general for the environmental review and the local government approval. So yeah.
Richard, do you have anything else to?
I do, because I'm sort of living this right now, and I have
Okay.
maybe some, maybe I'll offer them as informed thinking by my experiences so far. So one is, Gwen, as you and I talked about before,
Yeah.
this kind of event, like demystifying this technology, demystifying what it is, and letting everyone know, or helping to raise sort of a level of understanding. It's not a mysterious, scary black box. I mean, it's an engineered system. It makes heat. That heat is turned into electricity. It does it through nuclear fission as opposed to burning coal or burning oil. But it's not some mystical technology, and it has hazards, and benefits like any other technology. So I just think talking about it and helping people ask questions so they can really sort of understand, is really important as Alaska moves to adopt this technology. So demystifying, getting the public engaged, making sure there's addressing any misconceptions or fears about it. Alaskans, in my experience, are pretty practical set of folks. You live in a pretty harsh and scary environment. I grew up in Phoenix, so let me qualify what harsh and scary is. But there's so many energy needs in the state and a limited way to provide that energy. And so I think it's pretty clear to everybody there's some major benefits to this kind of technology.
Mm-hmm.
But the other things I'd offer, in terms of how the state is preparing, first, the state will play a role in sort of regulating these things. And so raising the level of education or understanding and having a conversation about what is the state's role in regulating these systems as they come into use and are get deployed. That's one thing the state can be doing to prepare. A second thing, which is often overlooked, is, as I mentioned in my earlier comments, the local emergency response capabilities. Let me talk about the fire department or paramedics. As we have worked with communities, there's just really practical questions like, hey, so there's going to be a microreactor here or a small modular reactor here. Does that change like how I need to train my firefighters or my paramedics? Are we going to need different equipment? If we respond to a fire or an accident at this site, are there things we need to know about rolling up on a microreactor or an SMR? So these are like very practical questions from the local community. Another thing that the industry will need is to lower costs around these reactors. They cannot have the standard security force that we do at, say, a light water reactor, which is it's a big place. It's got guards. It's got fences. That's not really practical for these small reactors. So a lot of these vendors and a lot of these deployment ideas are going to rely on partnerships with sort of local law enforcement to provide backup if something is happening, if someone's messing with one of these plants. Who do you call? You have to get these arrangements in place. But local law enforcement has the same questions, right? If I roll up to an incident or something that's happening at a microreactor, what do I need to know, right? How do I need to prepare? And so these agreements have to get in place for one of these reactors to really be brought up successfully into operation and to work. And so that's probably my message, is that the local community, the people, emergency services, law enforcement, the infrastructure folks, the folks that run your local grid, all have questions about what does it mean to have a microreactor and what's our role going to be in it. And these are wonderful conversations to drive in preparation for someone arriving. Oklo arrives with a Connex box that says Aurora reactor on the side, push green button, which is a cool idea, but there's a lot of stuff that has to be done to make that an actual useful part of the community. So those are the thoughts I'd offer.
Thanks, Richard. I'm going to tee off of that and go back to Lou with, when Lou, in your remarks, you kind of mentioned the importance, as Richard just also emphasized, of like kind of community engagement and education. You also kind of said in your remarks that you're kind of an unapologetic supporter of nuclear. You have some of the most familiarity of any Alaskans that I know with nuclear technologies. And one of the things our polling has generally found is that the more people know about advanced nuclear or new nuclear or Gen 4, whatever we want to call it, right? The more supportive they tend to be of at least considering this as an energy option. But we'll hear a little bit of our polling results from our most recent poll. There's still a lot of people that just don't really know what's happening or how things are evolving. And so it tends to be that the people most interested, most educated, are engaged, that are showing up for example, workshops like these. How do we kind of get the word out to more people so that at least they're making informed choices? If they're not supportive of nuclear, that's based on an informed perspective. And that's kind of a thing that working at a university, that's sort of what I want to see, is that I'm not necessarily saying that nuclear is the answer to everything, but if you're not interested in that, or you don't think that that's something that should be considered at all, that's coming from an informed perspective. Do you have any thoughts on like how we do a better job at getting a broader part of the public more aware of and educated on the technology?
Thanks, Gwen. So I've thought about this quite a bit because of being involved in any number of questions related to how would we potentially successfully deploy nuclear in Alaska, and I would say emphasize less the details of the technology. As engineering based folks, we tend to say it's safe because of this passive safety system, or it's more reliable because of this advanced fuel design, and speak more to the questions that people ask. What are you going to do with the fuel? So, I can't tell you how many presentations I've gone to where the speaker moves eloquently through a dozen slides. That's the first question, and it stops them dead. And I'm like, did you not see that coming? Didn't you know that was going to be the first thing they were going to ask? So you have to have a good answer. What are you going to do with the fuel? Well, at the end of the cycle, we're going to pick it up. We're going to move it. Here's how we're going to move it. We've got this all figured out with the regulators, and this is where it's going to go. Okay. And then you have to be able to answer very simple questions like, how is this going to affect, especially in more rural areas, how is this going to affect our ability to gather food? How is this going to affect fishing? How is this going to affect hunting? How is this going to affect berry picking? Well, so you can't explain that by talking about neutron energy, and yet that's kind of the first place that people tend to go, because that's their comfortable zone. So I think you have to kind of get out of, we as the technical folks need to get out of our comfort zone and meet people where their concerns are and engage them and hear what their real concerns are. I'm afraid something bad is going to happen because this thing is here. It's going to affect how I live and how I want to continue to live. And so we have to have pretty straightforward, honest answers about, no, it won't. And there are consequences to any form of energy generation, whether it's diesel generation, wind power, solar, what have you. You have to speak honestly about the consequences of it. But I think to hear people's concerns and to kind of meet them where they live, talk a little less about the technology and a little more about the real impacts on their lives. And I love that what Richard was talking about engaging the local community, because it's critical, right? So for these microreactors, emergency planning, I suspect, is going to be relatively very simple compared to what you have to do for large light water reactors. But you have to do it. You have to get the fire chief and say, if something happens here, here's how we handle it. It's just engagement and introducing people to the concept, and that it's not really, special technology. It's old technology, and we're just going to use it in a very beneficial way.
Neil, you guys went through a pretty extensive process through DEC with trying to collect perspectives from Alaskans. Do you have anything to say about what you learned from that, or how we could improve on those processes in the future?
Yeah, so we obviously, through any type of regulations change, we have public notice processes, we get feedback. In this particular case, a lot of the feedback we got was on nuclear safety. And the scope of our siting regulations do not cover any component of that. And so, a lot of the questions that the public have are going to be directed to, through the NRC process. And we made that clear. We want everyone to understand what our role is in this versus NRC's role. But yeah, I mean, a lot of it is providing the information, and as the state regulatory agency for the siting portion, I can't speak on behalf of any type of outreach that the state might participate in, or be willing to participate in. Obviously, we were given this task, and initiated by the governor, and so I mean, and the legislature. So obviously, that was a supportive thing. We're ready for to be a part of this process. How much engagement we have from the state side, I can't speak on necessarily. But I mean, I would mirror what everyone's saying. It's crucial to get that real information to the folks that are concerned. And like Lou was saying, the people that are asking questions, it usually is specific to, hey, yeah, what are you doing with this fuel? Hey, how is this going to impact my fishing? Will it impact my fishing? And really, those things are crucial, in having that clear plan and procedures in place, having the local engagement. And once again, we did incorporate this as part of our process, the local municipal approval or the legislative approval. And they are required through that process. They are required to provide public outreach. They're required to do public notices and actually have multiple meetings, so that this information, the applicant has the opportunity to provide that information to the public. And so we did try to incorporate more of that process, so that information could be provided to the individuals that have these questions. So we're hoping that will at least start that engagement process, and require that applicant to go through that process to try to help provide some answers to some of the concerns from the local community members in these situations. So yeah.
All right, thanks, Neil. I'm gonna do a couple of quick round questions now. So the first one, just could either Richard or Mark, this is for one of you, you decide who is better suited to take this, but could someone give us a little bit of an update or talk a little bit about nuclear fusion, please? Where are we with that?
I'm a fission guy, but it's there's a lot of excitement. There's a lot of companies out there. There happen to be several in kind of the Washington area, Seattle area. They're looking at it. There's a lot of hype. If there's reality behind the hype, I don't know yet. Maybe there is. DOE has, if you look at their latest organization chart, has moved fusion out from a program underneath the Office of Science to its own kind of office, on the equivalent line of all the applied energy offices there. So there's movement. I personally, I think there's a ways to go.
Yeah. Would you agree with that, Richard?
Well, I'm laughing. I'm a nuclear engineer, so if there are any
Yeah.
nuclear engineers in the crowd, the joke is, nuclear engineers always have to take a fusion class, and the professor always tells you fusion is only 30 years away. And so then the next generation of nuclear engineers grow up, become faculty, teach the fusion class, and say it's only 30 years away. So I, the joke aside, it's actually quite interesting. As Mark said, the DOE is organizing itself to really provide a focused investment in fusion, and science advances, right? And so if you watch the news, you'll see there have been a lot of breakthroughs in terms of creating what they would call a net energy generation out of these fusion systems. So you have to do all kinds of stuff to
That's
create fusion with lasers and high pressure, and it's a science fiction movie. But the trick is you put a lot of energy in, but once you start getting even more energy out, then it
which we
starts.
haven't done yet, right? That we
Yeah,
haven't
well,
done
no,
yet.
there's been breakthroughs. You get a bit more
Hmm.
energy out, so
Yeah.
it's tricky, it's hard, but we're chipping away at it.
Hmm.
I'm an engineer, right? So we're sort of chipping away at the problem. The thing that I watch, which is one of my indicators, is not the government investment; it's the private investment. And so, if you are paying attention to private companies that are pouring money into fusion, there's literally billions of dollars of private capital have been flowing into a lot of these companies that are trying to bring fusion systems into reality. And so they could be all people with way more money than they need. They're just tossing it down the toilet. But I tend to think when an area of technology starts to attract billions of dollars in investment, there's something there. So I will say, one of the roles we play for the NRC is actually beginning to help them think about how would they evaluate a license request from a fusion plant. It's a different, sort of different kettle of fish in many ways. So I will say, the NRC is beginning some preparations. You're seeing the DOE stand up offices and pile a bunch of money into it, and you're seeing private industry do it. So I would say that is one thing. I saw some of the comments, something to keep an eye on, right?
Yeah.
And I think we'd all be super. I would be super excited, if we could bring this technology to fruition and add it to the technologies we use to generate power for our country.
I just threw one link in the chat.
Yeah.
It's a Helion, and they're looking to build, their fusion reactors not far north of where our laboratory is.
There's a lot. There's a
Lot.
whole proliferation of like different companies. I did. This is a topic that we do want to park for the Alaska Nuclear Energy Working Group. So we've actually had Lawrence Berkeley National Lab speak to the group in the past, and so we'll make sure that we get this as a topic for the working group. We're gonna go to a break in a minute, but I do want to close up, Lou. You're the one, I think you were licensed but didn't serve on a nuclear powered submarine. Is that true? Is that
No, I was on a boat for 4 years. Yeah.
okay? Okay.
Yep.
So I'm curious, like when people talk about the nuclear navy, right? And so this idea that we already have these small reactors. Can you talk a little bit about how small reactors might differ from advanced reactors and how lessons learned from the Navy might apply to a more civilian applications, but it's quite different in terms of the fuel that we're using. And like, can you just like quickly just run through how they differ from what we might do on the civilian side?
After just admonishing everybody not to speak technically, I'm afraid I have to take a more technical turn, and that is that the U.S. Navy reactors all utilize highly enriched uranium, which would not be suitable for civilian use because of weapons proliferation concerns. And so they're compact and they're relatively powerful. There are evolutionary designs that are extraordinary when you compare them back to the first prototype that started in 1953. But the naval reactors are sort of a special case. Now you have to understand that the naval reactors jumped from the military to a plant in Shippingport, Pennsylvania, that became the prototype for civilian nuclear power in the US and then around the world, quite frankly. And so virtually all the large light water reactors are evolutionary designs based on the original naval reactor. one of two. One was sodium cooled, one was water cooled. We won't talk about the sodium cooled one, but they're all based on these evolutionary designs based on. So naval reactors kind of expanded and ruled the world, if you will, but many different reactor types were developed. And now some of the advanced reactors and the technologies that are being utilized in the microreactors are making good use of the technologies that were originally developed 50, 60 years ago, but now they've had much more design work done and advancements in fuel. So even though the naval reactors kind of were the ones that took over the nuclear world, this renaissance of advanced designs is really introducing other designs that I think are going to turn out to be very useful in the small and the micro range of power reactors, and are gonna be the ones that really take us to the next generation of nuclear power.
Gwen, can I add something real quick?
Yeah, go ahead.
I mean, nuclear's got, operators and people working at plants, a very strong safety culture. When you enter this industry, safety, as Lou said earlier, safety is the number one thing on your mind. Everything you do is about safety. The Navy does that in spades. And so one of the benefits, in addition to what Lou talked about, is the workforce that comes out of the Navy into the nuclear industry it's phenomenal. It's a great pipeline, to build that workforce.
All right. Well, thanks to all of you. I think we'll close out the panel with that. So thanks for that final comment, Mark.
Hang on. Are you
And
gonna do?
yeah,
I'm coming loud and clear?
you are, Jeff. We're just about to go into a 10-minute break, and then we are going to start up right after the break at 10:30, well, Alaska time anyway, sharp, with your presentation. So thanks for joining us, Jeff. We really appreciate your time. Jeff is with the Department of the Army, and he's going to give us an update from Project Pele to Janus. But first, we're just going to go into a quick break for 10 minutes. So, all right. Thanks, everyone. Appreciate the panel. All right. All right. I hope everyone had a good break, got a cup of coffee. Dr. Jeff Waxman, I am so glad that you could join us. I really appreciate you taking the time today. I know that you are incredibly busy. You are serving as the Principal Deputy Assistant Secretary for the Army for Installations, Energy, and Environment, which I think is about the longest title I have seen in a while. But you're basically advising the Secretary and Chief of Staff for the Army on everything from installation modernization and energy to environmental and infrastructure policy. So you've got a very broad portfolio. That's not your entire bio. So again, as I mentioned before, the full bio for all of our speakers are in the packet that you received when you signed up for the workshop. But I've had the pleasure of getting to know you, Dr. Waxman, and I've been following your work for a long time, and I am very consistently impressed by your thoughtful, big picture approach to deploying advanced nuclear in ways that benefit the military while also creating pathways for longer term civilian applications. So with no further ado, I would like to pass the stage over to you.
Thanks, Gwen. Always good to chat. Sorry I can't be out in Alaska this time, but Alaska came to me. I've got 8 inches of snow outside in Virginia here, which is why I am dressed casual and I'm talking to you from the basement of my house rather than being dressed in a suit and talking to you from the Pentagon. So it is what it is. And that's why, for those of you who are on 10 minutes ago, so I'm something with my baby in my lap. It's a much more at-home day today. So, if the talk goes sideways or get any very hard questions, the baby can come back. So that's always an option.
That's awesome. All right.
So we have some slides here. Gwen, should I plan to stop partway through, or would you rather I just run through the whole slide deck and then do questions at that point?
I think it'd be better to just go ahead and run through the whole slide deck. And if anyone has questions as Jeff is speaking, go ahead and drop them in the chat. Jeff, you don't need to keep an eye out for that. I'll do that, and then I'll kind of curate the Q&A with you. when you're finished. Okay.
Great, we'll do that. And I will also, I'm very aware that the basement lights I have behind me are harsh. And if I go like this, I look like a medieval
It looks
king.
fine. It looks
Yeah.
totally fine.
So
Yeah.
I'm going to try to keep my head in front of the light. I'm not completely backlit for this presentation. Anyway, appreciate, very excited to have the conversation. Alaska is so important to what we do in energy. So let's push the next slide and get through the deck. So I wanted to start off with, I know what is most exciting to everybody, which is Pentagon bureaucracy, because I have found that even the vast majority of people in the Army don't know how the Army is structured. And so you hear my job title that has like 37 words in it, and you go, what does that mean? So this is just really simple. Within all the services, you have a civilian side and you have the uniform side. And so you have a Secretary of the Army, and then you have a Chief of Staff of the Army. And then on the Secretariat, we have 5 assistant secretariats, one of which is Installations, Energy, and Environment. And so that is the one that I am the principal deputy for. And we have a lot of counterparts on the Army staff side. But just to kind of visualize that all the things that the Army does are really broken up on both the Secretariat side and also the Army staff side. And then those two parts work together. Next slide, please. So as we oversee, we are installations, energy, and environment. Our remit is actually even a little bit broader than that. So in installations, that means we oversee all the infrastructure. So things like building the border wall, we do, but also not just building barracks, but also the off-base on-base privatized housing, and just anything you need to build, we do. We also have not just energy, but also water, and environment not only covers environmental permitting, but also things like safety and occupational health. So it's a pretty broad portfolio that we have. Next slide. So in terms of energy, I like to use the quote, which has been attributed to many people throughout history, which is that amateurs talk tactics, but professionals talk logistics. Which is that when you're a kid and you study warfare and or you watch war movies or play with your toys, whatever, you tend to think that warfare is decided by tactical maneuvers, bayonet charges, all that stuff. And then when you become more of an expert, you realize that actually all of warfare is driven by logistics and supplies and food and energy and ammunition. That is what drives everything in all conflicts. And so we are seeking in this administration, in particular, energy dominance. And that means both installation energy and operational energy. And in the modern world, installation and operational energy are really blending, very little difference between them. There is no harsh dividing line between installation and operational energy. Next slide, please. So the only AI you're going to get in this talk is this AI image that I made, because I decided that one of the biggest misconceptions of any issue in the public sphere is how electricity works. In general, we are all terribly misinformed on how electricity works. We are taught the wrong thing, and it leads to bad energy policy. So in general, people think that electricity works like that image on the left, which is a bucket of water that we are filling with more water as we generate electricity. And as we use electricity, the water is coming out the bottom and pouring out. And you can see my superb AI skills to put that together. I'm sure someone else can do better. But anyway, the point is that imagery is all wrong. In fact, the electric grid has to be perfectly balanced at all times, to the millisecond. The electric grid has to be perfectly balanced at all times. There's no storing electricity to use later. It all has to be perfectly balanced. So in my room here, I was talking about these harsh lights behind my head. If I were to go a few feet that way and turn the switch or turn those lights off, instantaneously, the nearest power plant here will instantaneously generate a little bit less electricity to perfectly balance the grid. And it is a remarkable engineering that this works. This is, you would imagine, if I asked a kid today, how would you engineer that? They go, well, boy, you'd have to have this advanced computing that's tracking exactly how much electricity, exactly which lights are on everywhere in every building. But in fact, the electric grid has worked like this for over 100 years. And understanding just how exactly we make the electric grid balance at all times really helps you understand why the electric grid is the way it is. In the short summary, the bottom line up front of this is that all electric grids everywhere in the world are completely dependent on dispatchable energy, which is electricity that can be controlled and that has enough inertia that it can deal with any sort of small changes from moment to moment. So every electric grid in the world, despite what you may hear, is primarily powered by some form of dispatchable energy. So that's either some form of fossil fuel or nuclear or hydroelectric or geothermal. Those are your choices at the current time. Biodiesel is also dispatchable, but it's a pretty small fraction of anybody's grid. So it's a huge challenge, and we don't do ourselves any favor by the way that we misinform ourselves about how the electric grid works. Next slide, please. So this is just to kind of give an example of the energy challenge in the Pacific. So I'm just using Guam as an example. We're not doing anything special at Guam, but it's just to kind of show it's probably the island that has the most interest and the most attention in the Pacific. So it's important to think about. If you ever want to understand how big the Pacific is, I'm telling people in Alaska this, but buy a globe, like one of the the old-fashioned ones you could spin, and just turn it to the Pacific, and you will notice that you basically can't see any land. The Pacific Ocean basically takes up the whole side of the globe that you're looking at. And when you think about a place like Guam, and thinking about the prior slide, how do all these islands power themselves? And the answer in the Pacific is that they're all oil-fired. They all burn oil. So Guam gets effectively all of its power from oil, just as most of the islands in the Pacific are. But what is even more challenging is that we have no way to get American oil there. So the little ship icon you're seeing on the left, that is symbolizing where Guam's oil comes from, which is that it's being shipped from the Middle East through the Malacca Strait on foreign flagged commercial vessels. That's how it gets to Guam. It's just an immense challenge. And if any sort of conflict were to bubble up in the Pacific, the first thing that would happen is the Malacca Strait would close and that oil shipment would stop. So the challenge to power ourselves in the Pacific is, in my opinion, the biggest challenge that we have if we were to ever get into any sort of significant conflict out there. And so certainly this is something that has particular relevance for Alaska, because if we can come up with ways to start to leverage some of the natural, I know it's a nuclear talk, but to leverage some of the fossil fuel resources that Alaska has and bring them to help provide more resiliency to the islands that we have in the Pacific, that would be a bit of a game changer as well. And that's something that we're also involved in at my office. Next slide, please. So I always feel like this graphic is helpful to understand. And in fact, we could pull this back by even looking at things like batteries. Because we often hear about, well, why don't we, just use batteries to power things in the Pacific? And the short version is that if you take the best batteries in the world, the most advanced batteries that exist now, they're just coming off out of the research laboratories, they are about 2% as energy dense as diesel. So that's a lot better than they used to be. About a decade ago, the best batteries were about 1% as energy dense as diesel. They're now up to about 2% as energy dense. But the fact that they're still only 2% as energy dense as diesel is why you're not going to see electric powered tanks or airplanes or commercial airliners anytime soon, just because fossil fuel is so energy dense compared to anything that we can make artificially. But then if we look the other way, okay, how much more energy dense than diesel is uranium-235? The answer is it is 2 million times more energy dense than diesel. So it's just orders and orders and orders of magnitude. It is a staggering difference. A uranium fuel pellet the size of a dime is equivalent to 1 ton of coal or 3 barrels of oil. It's just tremendously energy dense. It's like science fiction. If we had never discovered nuclear energy in the 40s and we discovered it yesterday, the front page story in every newspaper today would be that we've just discovered a world-changing energy source that's going to power the future. It's a remarkable thing. And it's odd that we still sometimes don't realize how remarkable it is. Next slide, please. So as we talk about nuclear power and its relevance to the commercial industry, it's worth remembering that the Department of Defense, or Department of War, has a long history of driving technologies that eventually transform the commercial sector, and that's in a number of different areas. Things like, GPS and the internet are some famous ones, but another one is nuclear power. The first commercial nuclear reactor to ever be built, the Shippingport reactor in 1957, was built by the Navy using an aircraft carrier reactor design, and that design was then handed off to General Electric and Westinghouse and other companies to make it bigger and more efficient. To this day, most commercial nuclear reactors around the world are pressurized water reactors, light water reactors, and they are that because that is what Admiral Rickover chose for a submarine. And so the Department of War can, by the design decisions it makes, can really drive the commercial sector. Next slide, please. Okay, so this slide here is a few months old, but every time I update this slide, it gets worse. So the United States still leads the world in nuclear power. We have the best reactors in the world, and the naval reactors are the best reactors in the world. But we have basically stopped building commercial reactors, or at least up until this presidential administration, we stopped building them. And so the result is that we have forgotten how to build. The supply chains are not there. The workforce is not there. And so the United States, outside of naval reactors, has built 2 power-producing nuclear reactors from scratch since 1978. So that is 2 in the last 48 years. In contrast, China has 29 under construction right now. And their leading design is an American design. So it's not that they have better technology than us. It is just that they have the ability to make big things. They can do large-scale forging. They know how to do concrete. They know how to build big projects. And this is something that we are trying to get back to in America. This is a big focus of this administration. How can we build big things again? How can we bring industrial capacity back to the United States? So nuclear is just one piece of a larger effort to bring manufacturing and industrial capability back to the United States. Next slide, please. So the last time I was in Alaska and on stage with Gwen, we were here talking about Project Pele, which was my prior job. So in that job, I was overseeing the attempt to build the first Generation 4 nuclear reactor outside of China. This reactor is still under construction, a transportable nuclear reactor. It is 1 to 5 megawatts of electrical power with 3 years of power at full power without refueling. It's transportable on a C-17 or via truck. This reactor is being assembled now. So this is a very real thing. What you're seeing on the right, for instance, that is when we broke the heavy machinery you see in the middle right there. That was us breaking ground about 1.5 years ago at this point. And then on the bottom right, that's the truck that's going to be driving this reactor around in Idaho. And so the fuel has already been fabricated. In fact, this slide is also a few months old. It says that the fuel will be delivered to INL in fall 2025, and it was. We held a ceremony in the fall of 2025 when the fuel arrived. So this reactor is being built now. We anticipate that it will be completely fabricated and delivered to Idaho in late 2027, and will probably turn on in early 2028 to likely be the first electricity generating Generation 4 nuclear reactor to be built outside of China. Next slide, please. So that was all what we were doing up through the start of this administration, right? Project Pele is underway. It had actually started all the way back in the first Trump administration and continued on through the Biden administration. And that's great. That's showing, can we actually build a reactor? Do we know how to actually figure out how to design, regulate, actually build an advanced reactor? But then in May of 2025, President Trump signed 4 executive orders on nuclear power. He signed them on the same day. I had a big ceremony in the Oval Office. It's a very exciting moment for nuclear power. And one of those 4 was about nuclear power for national security. And that had a number of things in it, but one of it said that moving forward for nuclear power for installation and operational power in the DoD, that will be led by the Army, and instructs the Army to go ahead with a program of record, and that the Army should regulate those reactors. And so we took a few months to do that, to put that together. And then that should take us to the next slide, I think. Let's see. On the next slide. Oh, no, one more slide. So this is just explain that the Army has said, yes, we acknowledge the executive orders, and we're going to put together a plan to lead the United States and forward back to world lead on building advanced nuclear power and building out the supply chain and delivering nuclear reactors, not just as prototype, which is what Pele is, but actual operational systems to power Army bases, and leveraging all the learnings from Project Pele as well as all the other nuclear work that's been going on in the last few years. Next slide, please. So that led us to finally announce the Janus program in October. So on the far left of the image, that's me. Then in the center there is the Secretary of the Army, and then on the right of the picture is the Secretary of Energy. And the point of showing this image is to show that this is high-level Army support and attention. Secretary Driscoll was happy to make the announcement with me and say, look, the Army is really doing this, and this is going ahead. We are in source selection now. So if you work for a nuclear company and you bid, please don't ask me questions about it. But we are in source selection now for this program. Next slide, please. So how are we going to do this? I am constantly comparing nuclear power now to where rockets were 25 to 30 years ago. I used to work at NASA, and so I'm very familiar with how commercial space got going, through companies like SpaceX and Blue Origin. And so we're trying to model our approach on that. And it's recognizing a couple things. One is that while there are a lot of exciting nuclear companies, they have a lot of money and a lot of engineers, they still need some help. None of them have fully figured out what a design for a commercial system is going to look like. And once they build one, it's going to take some time to really perfect that. Second of a kind, third of a kind, et cetera. They're going to need some help getting through that. They're also going to need some money. None of these companies are going to be able to close their business case on their first of a kind. They're going to need some help. So we have stood up a very flexible contracting process based on the NASA COTS example, leveraging other transactional authority if you're a government contracting nerd. And it will be a process where we will choose multiple companies, and then those companies will have what we call milestones that they will receive milestone payments on. And if the companies are delivering and continue to hit their schedules, they will continue to receive money from us. If they are not performing, then we can pull them out of the program and inject new companies in. So it's a very flexible process to allow us to keep the best performers around. But we're going to try to take all the lessons learned and all the knowledge that we have, and then leverage all the knowledge that these new companies have developed, as well as all the private capital that they have been able to bring in. We also anticipate that there will probably be more private capital that will come in once we finally say, hey, yay, verily, these are the top companies. And so all that together, we are optimistic that we will first announce the companies later this spring. And then we hope to have construction begin no later than FY28. And then we will do everything that we can to get these reactors to turn on before the end of 2028, although recognizing that's a very aggressive schedule. But we definitely think that it's very realistic to get a bunch of reactors built this decade. If we move to the next slide, we actually have a map of the sites that we are considering. So we announced 9 installations that we're considering for this first round of nuclear reactors. In theory, other sites could be added at a later date, but we did a pretty rigorous process to decide what we think the top 9 options are. 8 of those options are in the contiguous 48 states, and then 1 of them is in Alaska at Fort Wainwright. So this is going to be a process where we will be down selecting companies and also down selecting sites at the same time. So we're letting the sites basically compete against each other. And then we also need to match specific companies with specific sites based on the technology, the geology, any utility relationships, et cetera. It's kind of going to be like an awkward 7th grade dance, matching everybody up. And so all that's going to be what happens over the course of 2026. So I believe that's my last slide. If we move to the next slide. Yeah, so I guess what I'm going to close with is why I named this program Janus. So for folks who know me, I love to name things after mythological creatures. So at NASA, my one um, accomplishment that has stuck with the agency is that I was the first one to come up with the name Artemis for the Artemis program. Obviously, Project Pele is a Hawaiian god, and then for Janus, Janus is a Roman god, and Janus is the Roman god of transitions. It's why the month of January to the transition of the new year is January, named for Janus. And the idea is that, okay, we've got prototypes going. There are a couple of prototypes being built around the country. Pele is the most advanced, but there are others. But we have to move past the one of a kind, science experiment museum piece. We need to move to an actual commercial product that can actually reliably provide power at an affordable price. And so that's what we're trying to do in Janus. These companies are not just going to build one reactor for us, they're going to build multiple. And we are hopefully going to get to an nth of a kind and get them to something that they can sell not only to us, but to other customers. And that's the vision. This is not an easy vision. This is a challenge, but we believe that if anyone can do it, it is the team that we have assembled. So I really appreciate the opportunity to talk. I hope that was fast enough that I kept your attention, and happy to take any questions or have any conversations that the group would like to have. Thank you.
Awesome. Thank you. Thanks, Jeff. I really appreciate that. And, I know you've been working on this concept of like an nth of a kind, like how do we get this to market by bringing the cost down? Because the first reactor is going to incorporate, there's higher risk, especially when from a cost, but all these unknowns. You've been working on de-risking the technology, identifying those sort of like high risk items. I think for Pele, as I recall, that was actually a lot around the procurement of the fuel. That was something that you identified as like a high risk, long lead time item. So you sort of worked with the companies to kind of de-risk that element. What else do you see as like now those kind of high risk, long lead time things that are going to really push out the timeline and bring up the cost?
Yeah, well, I mean, I think fuel is a good example because it gets to the point I had on a prior slide about the difference between kind of like PowerPoint slides and real things, which is that, we stood up our own line to make triazole fuel. That's in Lynchburg, Virginia. And that's where we made all the fuel for Pele. And about 5 years ago, there were a whole lot of nuclear startups that were all saying they're going to make their own fuel lines. And then they've slowly, one by one, realized that's way harder than they thought it was. It's very expensive, very complicated. And so they're mostly all coming around and trying to buy fuel from the very line that we stood up. But there's a number of other areas there. It's not just uranium. It's also things like high-level graphite production. Nuclear-grade graphite is very difficult. And graphite, natural graphite comes basically exclusively from China. Synthetic graphite is a petroleum product. You can get it from the U.S., but there's different flavors of it. But other materials. Forging is another big challenge. Basically, anything nuclear grade is difficult. People think, I know how to weld. I have these master welders. Well, they may be able to weld for commercial buildings, but nuclear grade welding is a whole other level. So this is where one of the things we're trying to do, even though we're going to have multiple companies in Janus, is we're going to try to combine the supply chains as much as we can. Because if every nuclear startup has their own parallel supply chain, none of them will ever get to nth of a kind. No one's going to invest out. But if we can have multiple companies buying from the same place, then that supplier can then scale up and make stuff cheaper and then hopefully drive the cost down for the units.
I mean, that just makes a ton of sense. And so, one of the things that the philosophy that you started with Pele, and it sounds like now you've really applied to Janus as well, is you're sort of starting with a big funnel at the beginning when you're talking about working with vendors and just kind of narrowing that down over time. And then you're kind of doing that with the site selection now as well, because you're not just looking at a mobile reactor anymore. So you've got these 9 sites. How does this competition process work both for the sites and for the vendors, like when you're looking at matching them up? How do you go about that?
Yeah, so the way we chose the 9 sites originally was the team created a little formula based on a few things. It was based on what are the energy challenges at those sites now? Do they have reliable or unreliable power? What do they pay for electricity at those sites? Are there any geologic challenges there? Earthquakes or whatever? Are there significant infrastructure challenges for plugging into the utility? Like, are we going to have to build, a bunch of substations to make this work or not? And then also, what is the political situation in the state? Do we think the local government and the state government are going to support, or are they going to be against? And so that's how we end up with the top 9. So as we try to narrow it down from the 9 to whatever the smaller number is, 2 of the new things that are going to come in is, one is going to be, are these sites willing to help out financially, right? Either tax breaks for the company or even grant money to help that happen. And that will certainly make us a lot more amenable if the local state governments want to put in money. We think some of them potentially are. But it also comes down to, are there any utility relationships? Certain nuclear companies either want to work with certain utilities or want to not work with certain utilities. And everything that we're going to do is going to be done arm in arm with the local utilities. So that could be part of the conversation as well. So all those things combined, we'll put it in the gonculator and hopefully be able to match the companies and the sites.
Well, yeah, and that kind of brings up a question that we had. I know you didn't listen in on the previous panel, but there was a little bit of a question there in terms of what states or local areas can be doing to sort of prepare for potentially being engaged or involved. So you mentioned reaching out or involving states, utilities, in like looking at these individual sites. And is that something like, to what extent is your team like coming into these 9 states or 9 areas or 9 communities and like really trying to make sure that we're informing and educating them about what you're doing with Janus and about the technology overall? To what extent are you sort of expecting states and utilities to be kind of proactive in terms of reaching out? Like, talk a little bit about the process. We do have a dog in the fight here, and so
yeah. Well, so as I was trying to explain on my opening slide, right? Yeah. So I am not the program manager of this program because I now have a much broader remit. But we have the plus side is we have a whole team now in the Army doing this. And so the working level, that team has already gone and visited all the sites, and they're continuing to stay in touch, like with the garrison commanders, local utility, et cetera. That is an open dialogue that exists now. But I will be, personally going out. I've talked about this like the last time I was here in Alaska. In fact, on one of my previous trips to Alaska, I gave the story about how I was at the airport in Anchorage, and I had to get like the government rate. They needed me to fill out a form, and it said, who's my employer? And I said the Pentagon. And they said, what's the phone number? And I said the phone number for the Pentagon. I don't know, but they insisted, so I just Googled the Pentagon DC phone number. And some phone number came up. I just put it in because, like, if Hertz wants to call whoever the person is, sorry. But the point it made to me was that there is no phone number for the Pentagon, and it's natural in some local community to wonder, well, if there's some problem, if we're worried that they're going to trample on some cultural artifacts or something, who do I talk to? Who do I complain to? I can't call the Pentagon. And so that's why it's important to have a face. And so for Pele, I was always going out there, meeting with the tribal leadership in the area, the local governments, and saying, hey, this is my phone number. This is who I am. This is my email address. If you have any concerns about what's going on the site, here's who you talk to. And that really, I think, eased a lot of the concerns. And so we would be doing the same things here. So the sites absolutely should have open comms. And if they don't feel that way, that, reach out to me and I'll make sure that they have those open comms.
All right. Thank you. So one of the questions we've got is just speaking about costs a little bit. So, that's like, if you're really trying to get to this place where the first of a kind, second of a kind are going to be very expensive, lots of unknowns. We're trying to get to what you call an nth of a kind, right? Design. Where can you describe like what you envision, like the trajectory of these costs being? Does that make sense?
Yeah. Yeah. So, there's a natural tension, which is that nuclear reactors, just in theory, are the bigger they are, the more efficient they are. It's just physics. And so the really big reactors are going to be cheaper than the little small ones, all else being equal. And so the really big reactors, like an AP1000, those are already very cheap. In fact, if you have large nuclear reactors on your electric grid, it correlates pretty well that if you have them, your electric grid is cheaper and you pay less for electricity. But recognizing that there's certain applications, I can't use gigawatts. Like I couldn't deploy a gigawatt nuclear reactor in Alaska. You guys couldn't use it, right? It's way too big. And so that's brought the commercial sector really now has moved towards SMRs, which are like 100 megawatts each rather than a gigawatt. And those are going to be a little bit more expensive than the AP1000s, but the hope is that it'll be cheap enough that it'll still be cost efficient in the grid in the near future. Microreactors are a significantly bigger challenge because they're smaller and they're going to be even less efficient. The hope is that if you build enough of these things, you start to bring those costs down dramatically because you start to go from everything being a one-off, custom, handcrafted thing to something that is more of an assembly line. So again, to use the space example, this is what SpaceX has done. SpaceX has brought a lot of the costs of rockets that NASA would struggle to get 5% cost reductions on. SpaceX gets 90%, 95% cost reductions. And so the hope is that we'll eventually get there. But certainly for these first few, these microreactors are going to be more expensive. And that's why we have a significant amount of money to try to close that business case. So I can't talk about exactly how much money we're going to have in the Janus program. You're going to have to wait till the president releases his budget. Well, it's supposed to be in February. It's definitely not going to be February. It's almost certainly not going to be March, maybe in April, whenever the president's budget comes out for FY27, you'll see that we have a significant amount of money to try to bring those costs down. But that is going to be the challenge. But as I think people know in Alaska, in these more rural, low energy areas, they're already paying more for electricity. So, I pay like 14 cents a kilowatt hour, 12 cents a kilowatt hour here in Virginia, but I don't need to be 14 cents a kilowatt hour to be market competitive at the edge of the Railbelt. It could be significantly more than that. So this is the balance, but I'm not going to sit here and promise that microreactors will definitely be 20 cents or 25 cents a kilowatt hour. I mean, we're hoping they will be there, but anyone who has full confidence in that is not understanding that there's risk. And so we just have to do the best we can and hopefully get those costs down.
We're going to hear from Oklo about the Eielson reactor project tomorrow, but I just wanted to point out like one difference that you really did with at least Project Pele is you decided to go like a DoD DOE sort of licensing approach for like kind of a test reactor, right? Versus like a fully commercial licensing approach, which is what Eielson or the Air Force chose to do. Can you kind of talk about like comparing or contrasting those approaches?
Yeah. So in law, you can license reactors with the NRC, the Department of Energy, or the Department of Defense. And they're all parallel authorities. And under law, the general definition is that if you're on the commercial grid, it's NRC. If it's a DOE project, DOE licenses itself. And if it's for military purposes, then the DoD licenses itself. And a reactor on installation that is powering the installation only has to be DoD licensed. I think there's a general agreement on that. If you have a reactor that's selling some of its electricity off the grid, then it gets in a gray area and it's not exactly clear who would regulate it. Back in the Biden administration, our feeling was that you want to avoid NRC licensing just because it's not really built for this. NRC licensing is built around large light water reactors. They've never done non-light water reactors. They've never done advanced reactors. And the Department of Energy is just a lot better place to do more experimental things. And so that's why we went with Department of Energy licensing for Pele. For the Army program, we've now been told in the executive orders the DOW must license itself. So that's what we're doing. And so the Army Reactor Office actually already existed. So people might wonder, hey, the Army hasn't had reactors in decades. Well, we do have a test reactor in White Sands. But that aside, we stopped powering anything with reactors back in the early 70s. But there's still an Army Reactor Office. It used to be much bigger. It's now much smaller, but still exists. And in fact, that reactor office has been moved. It now reports up through me. So we have it inside the organization. And we've been adding some additional talent to help us do this. We will be relying heavily on Department of Energy to do most of the technical work for us. But ultimately, the Army will be regulating itself. And I just think in general, even if you have a reactor that's selling some of its electricity off-site, it's really, really challenging to have NRC licensing inside the fence line. It creates a lot of difficulties. It also creates a lot of challenges with nuclear waste. There's going to be a significant challenge with that. One of our abilities under DOW licensing is that we can remove all the nuclear waste from our site when we are done. In fact, one of the requirements on Janus is that within 2 years of a reactor shutting down, all nuclear material has to be removed from the site. We will move all of it to a single Department of Energy site. We don't know exactly where yet. We're still negotiating that, but that will be where all the nuclear waste will go. So it's just a much cleaner and easier process, in my opinion.
Yeah, I should just mention, because you might find this interesting. We've been doing a series of polls of Alaskans, like asking them what their largest concerns are. And nuclear waste always comes up as like the number one concern. What is the long-term plan for nuclear waste? That does seem to go hand in hand with public support for, kind of accelerating these new reactor designs, it seems like. So just a comment. I
Yep.
imagine that's fairly widespread
Yeah.
perspective.
Yeah. So the tack that this administration is taking, which I think is the right one, is to combine the nuclear waste problem with recycling. Because the reality is that you can recycle nuclear fuel over and over and over again. In fact, commercial nuclear fuel, when they pull those fuel rods out, they typically burn something like 5 to 6% of the uranium-235. You could recycle it and use it a dozen times. We don't have recycling in this country. We shut it. Jimmy Carter shut it down and never got restarted. But recycling goes on every day in some of the other countries around the world. And so potentially, if you get this nuclear fuel, if you could recycle it, it's not just uranium you get out of it. You could also get out of things like medical isotopes. People don't realize that every day on the roads in the United States, there are tens of thousands of radioactive shipments every day in trucks, but they're almost all medical isotopes that are used for things like fighting cancer and doing certain medical tests. And you could pull those isotopes out of some of this nuclear material. So there's a lot of money to be made off of it. And so the idea is the DOE is looking for locations that they can set up a recycling facility, and what can be recycled can then be recycled and resold. And then the stuff that can't be recycled, the steel and concrete and stuff like that, that will go into either an intermediate or permanent repository.
I just have kind of pushed back on that just a little bit. That's true for conventional fuels that we're using in the nuclear industry. But when you're looking at TRISO, for example, which you've been very instrumental in making, the whole point there is that it's packaged, right, in these abrasion resistant and temperature resistant advanced materials. And so that's going to be a lot harder to recycle. That's kind of the trade-off, right?
Yeah, right. Yeah. So right now there's no real way to recycle TRISO fuel. But we would just be a small piece of the nuclear waste that's going to these sites. The vast majority of nuclear waste exists in the country at this high level waste is the leftover fuel at all the commercial reactors that we have. So if you go to any commercial reactor in the United States, what you will find is that they have the last 20 years of waste is sitting in these little casks out in the back. And that would be what you would recycle first. And that's also orders of magnitude more than anything that we're going to produce. So we would just be a small rounding error on a much bigger DOE effort for recycling.
Yeah, fair enough. Well, I just today I actually visited the Onkalo long-term geologic repository site here in Finland. I'm calling in from Finland, so it's pretty interesting, like how these different approaches or thoughts. I mean, they've been working on that for 40 years and are now just going to start basically putting nuclear waste in there this year, is what it looks like. So they've been pretty forward thinking on it. I have two questions I want to end with. Maybe we'll have a little bit of time for more. But one is, first of all, I've got a lot of questions in the chat asking, will you allow us to share your slides? That's one question that we have for you.
That's fine.
Is that okay? Okay. All right. That's great, because there's a lot of interest in that. And then secondly, I'd really like you to project us all forward 10 years. This is the kind of technology that we always are hearing. It's 10 years out, or it's 5 years out. Maybe we're closer now. I don't know, right? And so I'm curious, from your perspective, what's the best case scenario for this industry in 10 years? And what's maybe a worst case scenario? What are kind of those bookends that you sort of see that we might be at in 10 years with your crystal ball?
Well, I wish I had a crystal ball, because I'd use it to gamble. I don't know if you see what we make as government civil servants, but it's not a lot. But that all said, I mean, I'll just say, when I first got into this field, I read a lot of books about Admiral Rickover, who's the father of the nuclear navy. And he always struck me as just this incredibly crusty jerk. But the thing is, the longer I've been doing this, the more I sympathize and I kind of get it. So the point is I find myself in this weird position where I go around all the time promoting nuclear. I'm constantly giving talks. I spent the last 7 years of my life trying to make nuclear happen. I'm constantly going and arguing for why nuclear should happen. I'm a huge believer in it. But I also end up finding myself constantly trying to pour cold water on some ridiculous predictions by some of these startups that have to say ridiculous things in order to get funding. And so I always have to remind people that nuclear is very, very hard. That's why I have the slide on my slide deck. That's the nuclear power is hard slide, to recognize that. And to recognize that there is a chance that none of these advanced reactors get built. I mean, we just have to recognize that this could happen, right? We had a nuclear renaissance in this country 20 years ago, and in the end, only 2 reactors got built, right? Like that could be what happens. Now, I think that's unlikely, and I don't think that's what's going to happen. But we do need to recognize that the baseline is that, oh yeah, we're definitely going to have 50 reactors in the near future. Like that definitely may not happen. Now, that said, I'm optimistic. I believe that the Pele reactor will certainly turn on. And then I believe that the DOE crit tests are going to happen this year. And then I believe that some of these Janus microreactors will turn on before the end of the decade. So by 10 years from now, we should have a pretty good idea of if microreactors are going to work. Like either we have a handful of them that are already operating and the costs are coming down close to cost competitive, or not. We should have a pretty good idea by the end of the decade, or 10 years from now. And then in terms of full-size SMRs, the around 100 megawatts or so, I think the general consensus, if you talk to experts in the field, as I do a lot, that probably the first of those is going to turn on optimistically around 2030, maybe more like 2032. But hopefully by 2035, we at least have half dozen operating. We're starting to build that operating experience, and we've decided that yes, SMRs are a real thing, because while they're going to be a little bit more expensive than an AP1000, it's been very difficult to get AP1000s built. It's hard to get utilities to go, yeah, I'm going to take a $50 billion loan to do anything. In fact, certain utilities just don't have that kind of credit. They just can't do it. So if the SMRs can be even 15 cents or 20 cents a kilowatt hour, I think they will still be very successful. So I'm optimistic that 10 years from now, that's where we will be.
All right, I'm gonna take the liberty of asking you one more question. I'm sort of curious with both Pele and Janus. To what extent are you also working with vendors on the power conversion side? We keep talking about the reactor, but that's really just basically a glorified heat source in a way, right? So we still need to convert that heat into power, and there's a lot of innovation that can happen on that side too.
Yeah, no, that's a great point. So in fact, so I mentioned earlier Department of Energy crit test. So if you've been following nuclear in the news, you're aware that the Department of Energy is saying that they will have 3 reactors that will turn on by around July 4th of this year. And so to the point you're making, Gwen, those are just cores. So they're just going to be making a tiny amount of heat. They're not going to be making electricity. So in physics terminology, we're going to be making neutrons. There'll be radioactivity. It'll be warm, but there's no electricity generation. The power conversion side is not happening this year. That takes longer. And so we use a phraseology called balance of plant. We said you can't just build a nuclear core and then put a power conversion system and then attach pipes and then it just works. It's not that simple. It's a lot more complicated than that. And that's been a big part of the learning for all the teams that have been working on projects like Pele. But this is also the learning that's going to come of why I talk about nth of a kind. Because what people are going to find with any first of a kind system is that we all know pretty well how a reactor is going to operate, but that balance of plant can be tricky. And what you're worried about is that the reactor won't be as efficient as you're hoping it will be. There'll be some sort of engineering mismatch, or maybe it'll be more fragile than you think. And after you shut off the reactor a few times, something cracks or breaks. And that's all the learning that will come that will make the second of a kind and to the nth of a kind better and more efficient. So these first reactors are not going to be up 100% of the time. If anyone's first of a kind reactor is even up half the time, has a 50% uptime, that will be remarkable. But we know that the commercial fleet in the US now has a 93% uptime. So you can get these incredibly good uptimes once you build that practice. And so that is what we're trying to do. And that's where we hope to get to for these advanced reactors.
Awesome. Well, thank you so much for taking the time on a snowy day back out east. We really appreciate really appreciate everything that you're doing in this space. And I've really appreciate your very down-to-earth approach, both in working with states and stakeholders, and just think that you're doing a great job. So thank you for joining us today.
Thanks, Gwen. It's a pleasure.
All right. Okay, so we are next. We're going to bring up Spencer Klein from the Nuclear Energy Institute. So Spencer, I'm really glad that you could join us today. You have a tough act to follow, but I know that you're up to it. And I partly put you on the spot for this because you put me on the spot at the last Alaska Sustainable Energy Conference. I got to fill in for you when you got sick at the last minute there. So thank you for taking the time today. I think you've also got some weather challenges. Be interested to hear how that's going for you. But you're a senior project manager at the Nuclear Energy Institute, where you're working on improving the commercial and regulatory environment for deploying advanced nuclear technologies with a particular focus on licensing and authorization, which you are going to talk to us about today. And so again, you've got his full bio in the workshop materials you received when you registered, but we're glad to have you walk us through the evolving and very quickly evolving federal regulatory landscapes.
I'm Spencer Klein, Senior Project Manager at the Nuclear Energy Institute. So my goal today is to provide a clear end-to-end view of the U.S. nuclear licensing landscape, where it came from, where it stands today, and where it is headed. So first, we will set the historical context for U.S. nuclear licensing and regulation, highlighting how early statutory choices and major events shaped the system we operate under today. Then we will do a brief walkthrough of current NRC licensing frameworks, including the traditional pathways and how they have been applied in practice. I will then describe recent and ongoing regulatory reforms, including statutory, executive, and agency-driven changes that are fundamentally reshaping how nuclear reactors are reviewed and approved. And the presentation will also clarify the distinct but coordinated roles of the NRC, Department of Energy, and the Department of Defense in nuclear authorization and oversight, and explain how those roles interact in today's emerging whole of government approach, which Dr. Waxman himself touched on a little bit. So hopefully I don't give you guys too much of a duplicative presentation. And building on that foundation, we will highlight new and emerging licensing pathways that we expect will support advanced reactors, modular deployment, and high volume licensing. Lastly, we will assess the practical implications of these changes for applicants, developers, investors, and other stakeholders, and outline some key milestones to keep an eye on that will define the next era of U.S. nuclear licensing. So, to kick us off, let's look at where we started. From the 1950s through the 1970s, the United States undertook a significant number of nuclear projects spanning research reactors, defense applications like Dr. Waxman mentioned, and the first generation of commercial nuclear power plants. A foundational milestone was the Atomic Energy Act of 1954, which for the first time allowed private ownership and operation of nuclear reactors, making commercial nuclear power possible. This legislation established a dual mission for the federal government to promote peaceful uses of nuclear energy while ensuring public health and safety. As the civilian nuclear industry expanded, Congress re-examined how nuclear activities were regulated. The Energy Reorganization Act of 1974 separated promotional and regulatory functions by abolishing the Atomic Energy Commission, or AEC, and creating the Nuclear Regulatory Commission, establishing an independent regulator focused solely on safety, security, and environmental protection, while also giving some of those responsibilities from the AEC to the Department of Energy. The regulatory framework continued to evolve in response to operating experience and major events. The 1979 Three Mile Island incident, while resulting in no loss of containment and no significant radiation release to the public, highlighted the importance of human factors, emergency preparedness, and operator training, leading to lasting changes in U.S. regulatory practices. Subsequent global and domestic events further shaped U.S. nuclear regulation. The 1986 Chernobyl disaster underscored the consequences of poor design and weak safety culture. And after the events of September 11th, 2001, U.S. plants were upgraded to withstand blast effects, aircraft impacts, and deliberate threats. Following all this, the 2011 Fukushima accident, which prompted a comprehensive reevaluation of all U.S. plants for seismic and flooding hazards, building on work that was already underway at the time. And then, on a more positive note, we have the most recent completion of Vogtle Units 3 and 4, which signifies the first addition of new commercial nuclear reactors to the U.S. power grid in decades. Now let's take a little deeper into how the regulatory framework evolved as a result of some of these events, specifically 3 Mile Island. After the 3 Mile Island accident, the NRC fundamentally expanded how it regulated nuclear power plants. So the immediate response was the TMI action plan, which was later formalized into New Reg 0737, which translated accident lessons into enforceable requirements. A central lesson was the role of operators in the control room. This led to codified staffing requirements, enhanced training expectations, and the formal integration of human factors engineering into plant design and review. Emergency preparedness also became part of the licensing basis, with explicit regulatory standards requiring coordination among licensees, states, and FEMA to demonstrate reasonable assurance of public protection. And finally, among other things, NRC regulation expanded beyond traditional design basis assumptions. Rules such as the station blackout requirement reflected a growing emphasis on coping capability and defense in depth. Collectively, these changes, amongst the others, marked a lasting shift toward a more comprehensive, performance-focused regulatory framework that still shapes NRC oversight today. With the events of the past in mind, let's look at the existing NRC framework, which reflects decades of adaptation layered onto the original system. So today, nuclear reactors can be licensed, as most of us know, under 10 CFR Parts 50 or 52, and the NRC has invested heavily in developing technology-inclusive approaches for advanced reactors. Under 10 CFR Part 50, nuclear power plant licensing is a two-step process consisting of a construction permit followed by an operating license. And a construction permit, for those who may not know, is required before reactor construction begins, although limited activities may proceed under a limited work authorization. The construction permit application focuses on siting, environmental issues, and a preliminary safety analysis report. Importantly, under Part 50, the Commission does not approve final design details at the CP stage, unless specifically requested by the applicant, which historically allowed significant design flexibility during construction. However, this flexibility can also lead to rework and schedule risk if not managed appropriately. The second part of the process, the operating license, issued prior to operation, requires a final safety analysis report, technical specifications, emergency planning, and security plans. The NRC must find that construction has been substantially completed, and in practice, this process was deemed unpredictable by industry historically, and particularly when design or safety issues arose late in construction. To address these and other challenges that were raised by industry, the NRC established 10 CFR Part 52, which was intended to create a more standardized and predictable one-step licensing framework. Part 52 allows for early resolution of key issues, in some cases through design certification, standard design approvals, and early site permits, before a utility commits to construction, or even before the selection of a specific technology in the case of early site permits. The central licensing vehicle is the Combined Construction and Operating License, or COL, which authorizes both construction and operation in a single approval. That said, the licensee must show that inspections, tests, analyses, and acceptance criteria, or ITAC as we like to refer to it in industry, have all been met following construction and prior to fuel load. In parallel with these existing licensing pathways, the NRC has been developing 10 CFR Part 53, which is intended to be a technology-inclusive, risk-informed, and performance-based regulatory framework intended for optional use by commercial advanced reactor applicants. Part 53 is meant to better align regulatory requirements with the safety characteristics and risk profiles of advanced reactor technologies, including non-light water reactors, while maintaining the NRC's established safety principles. The current licensing framework under Parts 50 and 52, which we just briefly walked through, was developed around large, one-off light water reactor projects where long development timelines and bespoke reviews were and have been historically the norm. That model is increasingly misaligned with new demand signals emerging across the nuclear sector and from newly emerging end users for nuclear power. Advanced reactor developers are pursuing small modular reactors and microreactors, often designed for repeat siting, factory fabrication, and fleet deployment. These business models depend on high volume, repeatable licensing outcomes, and not single project custom regulatory processes. However, the existing model relies heavily on serial document-intensive safety reviews, where each application is treated largely as a standalone effort. Even when designs or issues have been previously reviewed, applicants have in some cases frequently faced relitigation of resolved safety and policy questions, which have driven cost, schedule risk, and some uncertainty. Fee recovery requirements have further compounded the challenge. Applicants have experienced uncertain review durations and unpredictable total licensing costs, which can be incompatible with private capital investment and commercialization timelines. So let's get into how that came about. Looking forward, scaling nuclear deployment will require a regulatory approach that emphasizes repeatability and standardization with bounded and predictable schedules. For proven designs and technologies, the review paradigm must shift toward review by exception, focusing on NRC resources on genuine safety significant changes rather than re-reviewing established conclusions. In short, enabling high volume deployments of advanced reactors will require evolving NRC processes to match the industrialization, modularity, and fleet-based deployment models that are now driving the market that we're in today, while preserving the agency's core safety mission. And I think it's safe to say that the NRC of today is not the same NRC of the past. I'm sure my industry colleagues would agree. They have made great strides to address the recommendations and innovations being brought to them, and I am hopeful that we will be pleasantly surprised when we see the NRC's newly revised regulatory framework, which I will discuss in upcoming slides. So before we get there, let's look at how everything came about. The Advanced Act of 2024 represents the most significant set of NRC-specific statutory reforms in decades, with a clear objective to modernize NRC regulation and accelerate the licensing and deployment of advanced nuclear reactors while maintaining safety. At its core, the Advanced Act directed the NRC to remove or modify certain longstanding constraints that no longer align with today's nuclear technologies or the deployment models we're looking at. This includes removing specific limitations on foreign ownership, control, or domination, where consistent with national security and safety considerations. The Act also requires the NRC to implement a suite of licensing efficiency initiatives, including reforms to the environmental review process, with the goal of reducing duplication, improving coordination, and shortening review timelines. Recognizing the unique characteristics of emerging technologies, Congress specifically directed the NRC to develop tailored licensing strategies for microreactors, as well as strategies to support timely licensing and effective oversight at brownfield sites, where existing infrastructure and environmental knowledge can be leveraged. To further improve predictability, the Advanced Act instructed the NRC to establish expedited procedures for reviewing qualifying new reactor license applications, moving the agency away from open-ended review schedules and toward bounded timelines. Finally, I'll mention that the Act addresses one of industry's most persistent concerns by directing changes to how the NRC recovers fees from applicants and licensees. This includes reduced hourly rates for advanced nuclear applicants and pre-applicants, helping to lower barriers to entry and support early engagement. In response, the NRC has already taken or proposed numerous actions to implement the Advanced Act, many of them aligned with the agency's parallel response to Executive Order 14300, which I'll discuss next. These reforms are producing measurable results, including more efficient and predictable licensing schedules. Recent examples come to mind, such as Cairo's Hermes Units 1 and 2, TerraPower's Kemmerer Unit 1, X-Energy's Longmont project, and TVA's Clinch River construction permit application, which all demonstrate that 18-month review schedules are now achievable, signaling a meaningful shift in how reactors are licensed in the United States. So as many of us know, in May 2025, as mentioned by Dr. Waxman in his previous presentation, the administration made a decisive policy intervention through a variety of executive orders, and specifically here, the Executive Order on NRC Reform, Executive Order 14300. This order reframes nuclear licensing not just as a safety function, but as a strategic enabler of energy security, economic competitiveness, and national security. It explicitly directed the NRC to modernize its approach to regulation in light of emerging reactor technologies and deployment needs, which is a critical shift. Licensing speed and predictability are now national policy objectives and not merely administrative goals. At the center of the order is a requirement for the NRC to conduct a comprehensive review and wholesale revision of its regulations and guidance on an accelerated timeline. So the intent there is to ensure that legacy requirements, many developed for large, first-of-a-kind light water reactors, as I previously mentioned, are updated to reflect current technologies, risk insights, and deployment models that we're looking at today. The order also calls for the establishment of fixed enforceable deadlines for NRC licensing decisions. This includes the maximum of 18 months for new reactor licensing decisions and 1 year for continued operations decisions, providing applicants and investors with predictable regulatory timelines. To avoid duplicative reviews, the order directs the NRC to create an expedited licensing pathway for reactor designs that have already been tested or demonstrated by the Department of Energy or the Department of Defense, as just mentioned by Dr. Waxman. Under this approach, NRC reviews would focus on incremental risks associated with the proposed commercial application rather than re-reviewing safety issues that were already evaluated in federal test or demonstration programs. Finally, the executive order emphasizes the need for a scalable licensing process to support high-volume deployment of microreactors and modular reactors, which is being codified under 10 CFR Part 57. This includes developing standardized approvals, leveraging design commonality, and considering the use of general licenses where appropriate. Taken together, among the other mandates within the order and the accompanying executive orders, the order signals a shift towards a more predictable, risk-informed, and scalable regulatory system aligned with the emerging nuclear technologies of today and deployment strategies being looked at by the end users. So, what we are seeing now is the transition from policy direction to concrete rulemaking. In response to the ADVANCE Act, Executive Order 14300, and related executive actions, the NRC is preparing an unprecedented volume of regulatory changes. In total, the regulatory reform is expected to include approximately 28 separate rulemakings. That's not counting the rulemaking for Part 53 when it's issued. And those 28 separate rulemakings collectively comprise more than 8,000 pages of regulatory text, guidance, and associated materials. Of these, roughly 17 are anticipated to be proposed rules, with the other 11 issued as direct final rules, reflecting areas where changes are expected to be less controversial, but that may not always be the case. Each rulemaking will follow the full federal rulemaking process, including commission approval and review by the Office of Information and Regulatory Affairs, or OIRA, as we refer to it, prior to publication in the Federal Register. Transparency and stakeholder engagement remain central features of the process. Each rule is expected to include a 30-day public comment period, and most will be accompanied by public meetings during the comment window to allow for real-time engagement and clarification with the NRC staff. For proposed rules, the NRC plans to publish red line markups where applicable, enabling stakeholders to clearly see how existing regulations would change. Substantively, these rulemakings are intended to address most, if not all, of the major reform elements identified in the ADVANCE Act or Executive Order 14300, as well as related executive and statutory directives ranging from licensing efficiency and risk-informed regulation to advanced reactor deployment and fee reform. In terms of timing, a couple of the rules have already been published, but the bulk of the proposed rules are expected to be published after publication of 10 CFR Part 53, with initial releases anticipated in the next month or two and continuing through the second quarter of 2026. The key takeaway is that NRC reform is now moving from high-level direction to a coordinated, large-scale rulemaking effort that will define the regulatory framework for the next generation of nuclear deployments. So let's take a closer look at the expected elements. This might be a little bit duplicative of previous comments, but I want to get you a high-level look at everything that we're looking at. As I mentioned, the NRC's wholesale regulatory review represents a top-to-bottom reassessment of the agency's regulatory framework, intended to align existing rules with modern reactor technologies, risk insights, and deployment needs. A central feature of the review is the move towards fixed licensing deadlines, paired with clear expectations for license durations and renewal processes to provide predictability for applicants and investors. Substantively, the review is expected to revisit radiation limits and credible risk assumptions, ensuring that regulatory requirements are risk-informed, performance-based, and proportionate to actual hazards for the designs being considered today. particularly for advanced and smaller reactors. The NRC is also expected to reform its NEPA approach, streamlining environmental reviews, reducing duplication, and better leveraging prior analyses, especially for repeat siting and brownfield locations. To support faster deployment, the revised framework is expected to include a pathway for expedited acceptance of DOE and DoD licensed and authorized reactors, allowing NRC reviews to focus on incremental risks rather than reevaluating work already completed and reviews by other federal agencies. Scalability is another core theme. The review is expected to enable high-volume licensing processes with clearer limits on design and licensing changes during construction, supporting modular and fleet-based deployment models. On security and safeguards, the NRC is expected to revise security rules, clarify materials security requirements, reassess import and export controls, and modernize transportation requirements under Part 71. The effort also spans foundational regulatory processes, including streamlining hearing procedures, clarifying the scope of ACRS reviews, updating operator licensing, and revising change processes under Parts 50 and 72. Several technical and cross-cutting updates are anticipated, including fuel cycle revisions under Part 70, code case adoptions, and updates to the IEEE standards. Finally, the review is expected to address reporting requirements, exempt licensing thresholds, reactor siting and decommissioning, and license termination topics, with the possible inclusion of various sunset provisions to prevent regulatory accumulation over time. So these elements reflect a shift toward a more predictable, scalable, and risk-informed regulatory system designed to support both safety as well as efficient, timely deployment of next-generation nuclear technologies. Taken together, the ongoing statutory, executive, and regulatory reforms have material implications for applicants, investors, and other stakeholders across the nuclear ecosystem. First, as I previously mentioned, applicants should expect fixed licensing deadlines for existing pathways to become the norm. 18 months for new reactor licensing decisions and 1-year reviews for continued operation of existing facilities, which represents a fundamental shift from the historically open-ended schedules to be bounded, predictable timelines. Second, the system is moving towards streamlined reviews of proven reactor designs, particularly those that have already been authorized or demonstrated by DOE or the Department of Defense. For these designs, NRC reviews are expected to focus on incremental risk and site-specific considerations rather than relitigating foundational safety issues. Third, reforms are pointing toward a new high-volume licensing pathway for factory-fabricated microreactors or equivalent modular technologies under Part 57. And for this, the conceptual target is first-of-a-kind licensing on the order of 12 months, with subsequent repeat applications potentially reviewed in 6 months, reflecting a shift toward fleet-based deployment models for nth-of-a-kind reactor designs. At the same time, applicants should expect modernized approaches to reactor licensing, safety oversight, and siting, including better use of existing data, risk-informed methods, and repeatable siting assumptions, particularly for brownfield and federal sites. Process reforms will also affect adjudication. There's expected to be greater flexibility in mandatory hearing requirements, along with streamlined contested adjudications, narrowing disputes to genuinely safety-significant issues. Environmental review practices are also evolving, with movement toward applicant-prepared environmental documents and consolidated NEPA reviews. For example, 1 applicant-prepared environmental document instead of 2, to reduce duplication of effort by applicants and the NRC, which results in extra time. For applicants, the strategic implications are clear. Standardization becomes a competitive advantage. So we want to push for high-quality submittals for standardized designs during licensing in exchange for dramatically improved predictability and speed. Finally, it's worth acknowledging, albeit somewhat self-servingly of me, that NEI and our colleagues across the industry have played a significant role in helping shape this progress. Industry work on our original proposal or regulation of rapid high-volume deployable reactors and remote applications addresses microreactor licensing frameworks, risk-informed and performance-based approaches, population-related siting density improvements, use of existing off-site seismic and meteorological data, licensing modernization initiatives, and environmental review reform, which has directly informed where the NRC and policymakers seem to be headed for these revisions to Parts 50, 52, 53, 57, and across the whole entire regulatory framework revision. Now, Dr. Waxman touched on it a little bit, but let's move beyond the NRC to look at the Division of Nuclear Regulatory Authority in the United States, which is grounded in the Atomic Energy Act and establishes distinct statutory roles for the NRC, DOE, and the DoD. Under the Atomic Energy Act, the Nuclear Regulatory Commission is responsible for licensing and regulating civilian nuclear power plants and certain other civilian nuclear facilities. This includes authority over reactor licensing, operation, safety, security, and environmental protection. The Act also allows for limited delegation of authority to agreement states, primarily for the regulation of certain radioactive material uses, as well as fusion now, but not for these typical power reactors. At the same time, the Atomic Energy Act explicitly preserves separate statutory authorities for certain federal nuclear facilities that fall outside NRC jurisdiction. These authorities form the legal foundation for DOE and DoD nuclear activities and underpin recent executive directed actions. For the Department of Defense, Atomic Energy Act Sections 91 Bravo and 110 Bravo provide authority for nuclear reactors and facilities used for military and national defense purposes. Under these provisions, reactors operated for defense missions, such as propulsion, military installations, or national security applications, are not subject to NRC licensing, but instead are regulated under DoD's internal safety and security frameworks. Similarly, the Department of Energy derives its authority from Atomic Energy Act Section 110 Alpha 2, which applies to nuclear facilities operated under contract with and for the account of DOE. This statutory authority enables DOE to authorize and oversee reactors used for research, development, demonstration, and testing, including advanced reactor pilot and demonstration projects. Importantly, these authorities are in addition and parallel to NRCs, not overlapping, as Dr. Waxman mentioned himself. DOE and DoD authorization does not replace NRC licensing for commercial use, but it does provide a lawful pathway for federal testing and operation outside NRC jurisdiction. This statutory structure explains how DOE and DoD can conduct reactor demonstrations today, while the NRC remains the independent regulator for commercial deployments. In short, the Atomic Energy Act establishes a tiered regulatory ecosystem. NRC regulates civilian commercial nuclear power. DOE and DoD regulate certain federal reactors under explicit statutory authorities, creating the legal foundation for today's coordinated whole-of-government nuclear strategy. So let's take a closer look at the DOE. The Department of Energy is playing an increasingly important role through the reactor pilot program to create a new pathway for advanced nuclear reactor testing and authorization under DOE authority. This initiative launched in response to Executive Order 14301, titled Reforming Nuclear Reactor Testing at the Department of Energy, which leverages DOE's statutory authority under the Atomic Energy Act to authorize reactor projects outside of the traditional national laboratory system. The program is designed to expedite research, development, construction, and operation of advanced reactors by allowing private developers to build and operate DOE-authorized reactors without requiring an NRC license for those demonstrations. Participating companies are responsible for all the costs, design, construction, operation, and decommissioning, while aiming to achieve criticality for at least 3 of these reactors by July 4th, 2026. DOE issued a request for applications in June 2025, with initial submissions due in July 2025, and future selections would be made on a rolling basis. The pilot seeks designs with reasonable prospects for operation by the 2026 target date, assessed on criteria including technological readiness, site evaluation, financial viability, and plans to achieve criticality. DOE has selected a cohort of advanced reactor companies to participate in the first phase of the program. While reactors under this pathway are not licensed by the NRC, DOE authorization is expected to provide a fast-tracked pathway toward future commercial licensing by the NRC by demonstrating performance and operational experience. In essence, the reactor pilot program represents a new model for early demonstration and risk reduction aimed at unlocking private capital, accelerating technical maturity, and smoothing the transition to the NRC's commercial licensing framework. Now let's take a complimentary look at the Department of Defense's approach to nuclear energy for defense missions that are grounded in Executive Order 14299, titled Deploying Advanced Nuclear Reactor Technologies for National Security. This executive order establishes a clear statutory and organizational framework for how nuclear reactors will be authorized, regulated, and operated within the Department of Defense. As my friend Dr. Waxman mentioned right before me, under the order, the Secretary of Defense, acting through the Secretary of the Army, is directed to establish a program of record for the utilization of nuclear energy to support both installation energy, powering domestic military bases, as well as operational energy, which supports deployed and mission-critical defense operations. The order further requires that the Secretary of Defense, through the Secretary of the Army, commence operation of a nuclear reactor regulated by the United States Army at a domestic military installation no later than September 30th, 2028. This milestone reflects a shift from concept and demonstration towards actual operational use of nuclear power within the defense enterprise. To ensure unity of effort, the order designates the Secretary of the Army as the executive agent for both installation and operational nuclear energy across the Department of Defense. This centralized government structure is intended to streamline decision-making, oversight, and technical standards while maintaining accountability for safety and security. Implementation is expected to proceed in phases. The installation energy program is expected to move first, using a contractor-owned, contractor-operated model for reactors located at domestic military installations under the Janus program, as mentioned by Dr. Waxman. This approach leverages private sector expertise, accelerates deployment, and reduces near-term burden on Army personnel. The operational energy mission is expected to follow later and is expected to be a government-owned, government-operated model, reflecting the additional complexity of operational requirements. These include deployability, survivability, force protection, and the potential for overseas operations, which demand deeper integration with military command structures. This phased approach also serves a practical purpose. It avoids overloading reactor vendors and Army teams during early implementation, allowing lessons learned from installation deployments and Project Pele to inform the more demanding operational mission. In combination, Executive Order 14299 establishes a clear pathway for DoD nuclear energy deployment, one that is mission-driven, phased, and aligned with national security requirements. With that in mind, let's take a closer look at the Army's reactor program that Dr. Waxman touched on, given the Secretary of the Army has been deemed the executive agent for both installation and operational nuclear energy across the Department of Defense. The Army reactor program traces its origins to the early days of the civilian and military nuclear enterprise. It was established under the Atomic Energy Act of 1954, supported by a presidential directive issued by President John F. Kennedy, which recognized the role of nuclear energy in supporting national defense missions. From its inception, the U.S. Army has overseen its own nuclear reactor operations, operating under statutory authorities that are distinct from but complementary to those of the NRC. This long-standing experience forms the foundation for today's Army-led nuclear energy initiatives. The Army reactor program is governed by a dedicated regulatory framework managed primarily through Army Regulation 50-7, Army Reactor Program, and Army Regulation 50-5, Nuclear Surety. Together, these regulations establish requirements for reactor safety, security, personnel reliability, emergency preparedness, and oversight across all Army nuclear reactor activities. While the Army regulates its reactors internally, Army regulations are aligned with NRC regulations and requirements to the maximum extent practical. This alignment reflects a deliberate effort to incorporate civilian nuclear safety principles, risk-informed practices, and lessons learned from the commercial nuclear sector. To further modernize the program, the Army is currently rewriting Army Regulation 50-7. The update is intended to incorporate best practices from the Department of Defense, the Department of Energy, and the NRC, reflecting the evolving landscape of advanced reactor technologies. Consistent with approaches used in the DOE Reactor Pilot Program and Project Pele, it is expected that the NRC will participate as an observer in Army reactor activities. This supports the executive order directive for the NRC to help streamline DoD and DOE reactor licensing while preserving clear lines of regulatory authority. And at the center of this framework is the Army Reactor Office that Jeff mentioned, which issues and manages permits for all Army nuclear reactor activities and sites, providing centralized oversight and accountability. In sum, the Army Reactor Program combines decades of operational experience with a modernized regulatory framework to support safe, secure, and mission-ready nuclear energy for national defense. With all that upset in mind, excuse me, the future nuclear licensing ecosystem is moving toward a more integrated whole-of-government approach, with the NRC, DOE, and Department of Defense working in coordinated but distinct roles to support timely reactor deployment while maintaining safety. Under recent executive orders, DOE and DoD are authorized to test, demonstrate, and operate advanced reactor designs under their own statutory authorities. These programs, such as DOE's Advanced Reactor Pilot Initiatives and DOE's programmatic efforts, are intended to establish technical viability and operational experience. Consistent with NRC guidance issued in December 2025, the NRC is not a decision maker in DOE or DoD authorization processes. However, the NRC will increasingly engage early and observe selected portions of those processes at the applicant's request to build familiarity with the technology, safety case, codes and standards, and operational assumptions being developed. This engagement is treated as pre-application interaction for the NRC, designed to improve efficiency and later NRC licensing reviews for the technologies. In this future model, DOE and DoD serve as front-end technology and demonstration partners, while the NRC remains the independent safety regulator for commercial licensing. When a developer later seeks an NRC license, the agency is expected to leverage prior DOE or DoD authorizations, focusing its own reviews on incremental risks associated with the proposed commercial application, rather than re-reviewing safety issues already addressed through federal testing and demonstration programs. To support this approach, the NRC, DOE, and DoD are coordinating on information sharing, regulatory crosswalks, and aligned engagement milestones, enabling applicants to transition more predictably from demonstration to commercial deployment. Taken together, this ecosystem is intended to reduce duplication, improve regulatory efficiency, and enable scalable licensing of advanced reactors while preserving clear lines of authority and the NRC's core safety mission. In closing, as we look ahead, several near-term milestones will signal whether the current reform momentum translates into durable change. We expect the NRC to begin publishing draft proposed rules in the first half of 2026, with final rules targeted by November 2026 for implementation. These rulemakings will operationalize many of the reforms discussed today, turning policy direction into enforceable regulatory practice. At the same time, DOE reactor pilot program projects are expected to reach initial criticality on or before July 4th, 2026. These demonstrations will be an important proof of concept, providing real operating data and experience that can be leveraged into future NRC licensing actions. Looking to the medium term, attention will shift to the Department of Defense. We anticipate DoD selection of reactor vendors for formal DoD authorization, particularly for installation energy applications, marking the transition from planning towards execution for those sites that Dr. Waxman mentioned in his presentation. In parallel, the NRC is expected to implement a streamlined, proven design licensing pathway, enabling applicants to leverage DOE-authorized reactor demonstrations and focus NRC reviews on incremental, site-specific risks rather than relitigating established safety cases. We also expect to see the first high-volume licensing precedents emerge, potentially under the new 10 CFR Part 57 pathway, signaling a move toward repeatable, fleet-based approvals rather than one-off licensing decisions. Stepping back, the broader takeaway is this. The next era of nuclear licensing is defined by leverage. Leverage of existing or prior reviews and data, leverage of demonstrations and operating experience, and leverage of standard designs into repeatable, scalable deployments. If these elements align, licensing can evolve from a bottleneck into an enabler, supporting timely, predictable deployment while maintaining the NRC's core safety mission, as well as the missions of the DOE and DoD. With that, thank you all for your time and attention, and thank you for allowing me to continue the conversation on the regulatory landscape for new nuclear. I will now yield any remaining time to the audience for questions or remarks. Apologies for taking so long.
Well, and Spencer, I assume that we'll be able to post your presentation because you have a lot of information in there. Is that okay?
There's a lot
Can we
going
share it?
on.
There is a lot going on. Yeah, and we don't have too much time left for Q&A, but I do want to just ask you a couple questions. One is if you don't mind, would you be willing to kind of talk just briefly about NEI's role as sort of the trade organization, right, with regard to working with the NRC? I'm just kind of curious in terms of some of this policy, what you see your role in terms of advocacy is being. And I'm assuming based on your presentation that the industry is pretty happy with the direction that NRC is going right now. Would that be fair to say?
I think that would be fair to say. And I think most of industry, not all of it, obviously, is aligned on what we have proposed to NRC in terms of reform for what's going on. We at NEI have previously submitted an accelerated NRC reform report that had hundreds of reforms that would optimize the existing regulatory structure, and that's publicly available. That's out there if anyone wants to Google it. But our role in that is we have regular touch points with our colleagues at the NRC on various subject matter topics to provide our member organizations recommendations on lessons learned from projects they've done themselves, whether it's licensing or operational. And we've developed regulatory guidance, for instance, where maybe there is a gap and regulatory guidance doesn't exist. One example of that is early site permit renewals. There's a number of our member utilities who have existing early site permits. They're coming up for expiration, and so there wasn't any existing guidance available. NEI, as one of the lead policy and regulatory organizations in the industry, we work very closely with NRC to provide them with regulatory recommendations and guidance on ways that the existing regulatory framework can be optimized. And we expect to continue doing that even after the new wholesale review of their regulations and guidance is issued at the end of the year.
Thanks. Yeah. So just a couple more quick questions. I'm going to put you on a spot here. I'm not sure if you know the answer to this, but does NEI have a position in terms of a long-term permanent repository for spent nuclear fuel? And regardless of whether you do or not, can you explain to the audience, if you know, sort of like who owns the spent nuclear fuel in the US? Can you explain that?
Who owns the spent nuclear fuel? I guess, I mean,
who's responsible for it?
Yeah, by statutory authority, DOE is expected to take the spent nuclear fuel, and that's written into law. And I guess we at NEI, I'm not going to say we have a specific position on it. Obviously, we support our members. And in some cases now you have state level communities that have their own thoughts, and some are willing to even be agreement states and take this spent fuel and be their own state level repository, as opposed to waiting on, let's say, a Yucca Mountain or some other DOE owned and operated long-term spent fuel repository. So there's a lot of shifting in the thought of what we're going to do with spent fuel. And even now, looking at recycling, that's another thing that people are looking at. I'm sure that our friends at Oklo up next will be discussing some things like that as well.
Mm-hmm. Okay. And the specific question is like, does that impact the NRC licensing at all in any way? The fact that we don't have a long-term plan or repository?
I mean, it's taken into consideration. Spent fuel is taken into consideration as part of the plans that you incorporate into the licensing. Do I think personally that it affects it much? No, because right now, I mean, if you look at the amount of spent fuel we have from the decades of operations of nuclear power plants, you could probably fit that on one football field. And there haven't been any type of accidents regarding spent fuel sitting there on a pad or in these ISFACs. So I personally do not think spent fuel is an issue, but it is one that we need to address and figure out our long-term solution for.
And another question, in terms of like attrition of expertise and staff at NRC, how do you feel that that's going right now? It feels like in past years there's been some attrition. Do you think that that's a concern, or are they able to are they pretty fully staffed right now? Do you have any sense of that?
If you look at LinkedIn, for those of us who follow the NRC, there is a lot of turnover at the NRC right now. And that's not even they're leaving the industry. They're just moving from NRC to our friends at the advanced reactor developers or other organizations still in the industry. So the expertise is still within the nuclear industry, but specific to NRC, I think the attrition is still there. There's still new hires that have new expertise and a great view on where we're going. So I think where we're currently at, I'm comfortable with the leadership we currently have in place with the NRC. I'm glad of the directors, deputy directors, and all those that are currently in place with the leadership at NRC. They've been doing a great job, and they have great views for what this regulatory reform is going to look like and what the future of NRC licensing and deployment is going to look like. So I'm pretty confident, but obviously more help is always going to be needed, especially to help support these DOE and DOD authorization pathways and be able to work together in a coordinated fashion.
So another quick question, and I think we'll have to wrap up here, but do you know, is there a current roadmap for advanced nuclear technology development for the US as a whole?
So I guess that depends on what you want to call what you want that roadmap to look like. So EPRI, the Electric Power Research Institute, does have a U.S. advanced reactor roadmap that NEI is a contributor and a co-author of. So if there's a specific roadmap you're looking for, I would Google the EPRI U.S. Advanced Reactor Roadmap.
Okay. All right. Well, thank you very much for joining us, and I hope you get your power back soon. So,
you and me both.
all right. Well, sounds good. Well, thank you. Thanks a lot, Spencer, and please keep in touch. So, yeah.
Absolutely. Thank you,
All right.
everyone.
Okay. So to wrap up today, I have asked David Correns. Oh my gosh. Cornerens? David, I'm so sorry. I should have practiced in advance. I'm just call you David. David is the Senior Vice President of Research at Strategies 360, and we've had the pleasure at ACEP of working with David on our latest round of public polling on energy issues for Alaska with a special kind of focus on nuclear. And so we've asked him to join us here at the end of today to kind of walk us through pretty hot off the press results from this latest round. And so I just want to thank you. I really appreciate, David, your very thoughtful kind of data-driven approach. You can find David's full bio in the materials you received, just like I said previously. But with that being said, do you want to go ahead and walk us through kind of a high-level version of your results? And then we'll publish the full version of these later. But right now, this is more specific to nuclear. The full survey includes broader topics as well. So I'll turn it over to you.
Great. And we at Strategies 360, especially on the market research team, have enjoyed working with ACEP over the past 3 years. And we have roughly about 20 slides, a little less than 20 slides. So we should have plenty of time for question and answer. So any that are coming up during the presentation, we'd ask you to put it in the chat, and then Gwen can help facilitate once we're done. So as I said, we've been conducting statewide research in Alaska since 2023 with ACEP. Each time there is a creative, interesting wrinkle. And this time that was conducting oversamples within Nome and Kotzebue. So what we will be talking about today derives from a survey of 400 adult residents statewide in Alaska. Those interviews were conducted with live interviewers calling landlines and cell phones, plus texted out invitations to take the survey on a web browser. Those statewide results, which will be most of what we're talking about today, because we can really jump down into specific regions and specific ideologies and gender splits. Those statewide results have a plus or minus margin of error of 4 percentage points. So, for example, if I were to say that 50% of residents statewide hold an opinion, the true percentage could be anywhere from 46 up to 54%. We additionally pursued what was a pretty aggressive and bold challenge of interviewing within specifically Nome and Kotzebue. Those oversamples of 50 adult residents within each have a margin of error plus or minus 14 percentage points. Again, this is a challenge, but one we are glad to take on. So we will not be diving into the subgroups within those, just because the margin of error would explode even further beyond 14% plus or minus. But we are only able to conduct this research in Nome and Kotzebue because we additionally layered in printed surveys that were mailed to residents that they could take. So for those survey respondents, they had upwards of 4 different methods to take the survey, which is really the gold standard of how to complete survey research in a representative manner, is to meet, in this case, residents where and how they prefer to engage in survey research. So here we have some illustrations of what it means to be representative of adult residents age 18 plus in Alaska statewide, broken down by gender, age, college attainment, geographic region, and self-identified race and ethnicity. These are all based off of US Census distributions, and they help ensure that what we are providing in terms of research is representative statewide. So if we move into our first section that we have here, we have the energy priorities of residents statewide, meaning should we be using the following forms of energy generation, more, about the same, or less? And what we found is that on a statewide basis, residents believe that hydroelectric, solar, wind, and waste to energy should be used more. Strong majorities of residents believe each of those methods. There is a scant or borderline majority that says Alaska should be using more nuclear power, 50%. Views on whether to use more, less, or about the same in terms of natural gas are the most varied and I think we could say conflicting. There is again a scant majority of residents that are saying Alaska should use less coal power. And so that is what it looks like from a statewide perspective. When we jump into specific subgroups, we can see that there are some clear divisions using ideology. Again, that is based off of a survey response. So survey respondents were allowed to self-identify. And what we can see is that residents who are more likely to identify as liberal or moderate were also more likely to support expanded use of solar and wind. Residents that were more likely to identify as conservative were more likely to support expanded use of nuclear and gas. Although even for nuclear power, almost 50% of self-identified liberals statewide support expanding that use. Residents, really, regardless of ideology, region, race, all support the expanded use of hydroelectric. And then conversely, residents, really regardless of geographic region, race or ethnicity, or ideology, would support using less coal or not more. Really, the high watermark there is self-identified conservatives, and even there, only 40% of them support using more coal. The red and green call-out boxes further up show some of the highs relative to the statewide averages and some of the lows. But this continuum for certain options on the liberal to conservative scale, again, self-identified based on survey response, was one of the more interesting findings that we found. So then moving forward into some specific questions around the use or awareness of nuclear power in the state, we first asked very broadly, from what you know now, do you support or oppose the idea of using nuclear energy in Alaska? We saw a strong majority saying 58% of residents statewide saying they do support using nuclear power. Again, this is support oppose rather than use more, use less, or about the same. When we asked within Nome and Kotzebue, there are higher levels of not sure or don't know in those areas, but still slightly more than support, slightly more support than oppose. 40% saying they'd support the use of nuclear power statewide within Nome, and 42% within Kotzebue. Looking at this broken down by region and by age, political ideology, and gender, we can see that there are that same kind of continuum where conservative, self-identified conservative residents are more likely to support. There's still 55% of self-identified liberals who say they support the use of nuclear power, and then moderates are a lower rate because there's just a higher not sure percentage. Then looking at that over time, which is what our 3+ year relationship with ASAP allows us to do, we can see this exact same question that we asked in previous years gives us a view that support has moderately increased from about 50% upwards of 60%, and then has kind of plateaued at 60%, or roughly 3 out of 5 residents saying they support. Opposition hovers around roughly about 1 in 3 residents remaining opposed. So there's been some slight movement, but overall largely static. Now, when we dove slightly deeper into the substance around nuclear microreactors or nuclear advanced microreactors, we first asked a simple awareness. Have you heard about a new type of nuclear technology called advanced microreactors? We found that only 40% of residents statewide have heard a lot or some about advanced microreactors, compared to 55% of residents statewide saying that they've heard nothing or only a little. That's broadly consistent across the state geographically. Older residents slightly likelier to say that they've heard something about this, but pretty consistent. Within Nome and Kotzebue, the have not heard rate or have only heard a little rate is even higher at 78% within Nome, 71% in Kotzebue. And then looking at this over time, because this is another question that when partnering on multiple rounds of research, we can ask multiple times to see change. We can note that there has been an increase in awareness, likely reflecting the hard work and community engagement that ASAP has been conducting. So there's been an increase in the percent of survey respondents from 26% increasing up to 40% now. However, the heard nothing or heard a little rate is still above 50%. So still a majority, but there is some positive progress and an increase in awareness reflecting the work that ASAP has conducted, engaging the community. We then got even more specific and asked about awareness in terms of familiarity or unfamiliarity, and if familiar, then favorable or unfavorable towards a specific microreactor at the Eielson Air Force Base. 2 out of 5 Alaskan residents have not heard of this specific project. However, of the majority that have heard about this project, there is more favorable opinions, 36% of residents statewide, then compared to unfavorable, only 13% of residents, with an additional 10% saying that they are familiar with the project or the microreactor, but they don't have an opinion or they are neutral. We then provided a fuller statement of context, keeping in mind a few slides ago we showed that there is more residents than in 2023 who have heard some or a lot about microreactors, but it's still less than a majority. We provide much more context in this paragraph, which I'll go ahead and read. As you may know, a nuclear microreactor is a small nuclear reactor that is much smaller than conventional nuclear technology. Microreactors are essentially a small nuclear-powered battery. They vary in size based on the manufacturer, but in general, will be small enough to fit inside a shipping container and produce around 10 megawatts, which could power 7,000 homes and also provide heat. Because of the small size, microreactors use much less nuclear fuel and cannot melt down. They also do not require water for cooling. After learning this information, do you support or oppose the idea of Alaska exploring the use of microreactors to supply energy to Alaskans? We found that more than 3 out of 4 residents, almost 4 out of 5 residents, after finding out this information, have a supportive opinion towards the concept of using nuclear microreactors. And this is consistent over time. Every time we've asked this exact same question with this exact same context, we receive a result that's in the realm of 3 out of 4 or at most maybe 4 out of 5 Alaskans saying they support the concept. Breaking that down by region and age and ideology and gender, we can see broad agreement, broad support that's pretty consistent after receiving that description, which some may have feedback for us on this call, but is specifically meant to describe in layman's terms what nuclear microreactors are and what the advantages of them would be if widely used. And so with that, those are all the slides we have for today. And I can go ahead, stop sharing, and take questions.
Yeah, I really appreciate that, David. And one thing I might just want to clarify is why we included Nome and Kotzebue specifically. And so what we've been doing is tagging this polling onto funded projects that we have, because we don't have any specific funding through the state of Alaska for looking at nuclear. And so we did have some funding through the Department of Energy to work with the communities of Kotzebue and Nome on sort of some stakeholder engagement, some local education, working with the schools and things like that. We worked with the tribes in Kotzebue and then Coeric, which is like the regional tribal consortium in the Bering Straits region. And so that's why we selected those two communities to do like a little bit of an oversampling on as a representative of rural communities that, you know, are of sufficient size that it would at least be worth looking at or considering a microreactor. There's very different local perceptions around nuclear, and so we did a lot of local surveying, but we wanted to get a more general snapshot from the community as a whole. And so I just want to kind of share why Nome and Kotzebue were sort of selected for that oversample. I actually don't see any questions for you, so I don't know. That's I guess we've actually tired people out today or something like that, David, but I really appreciate you sharing all of that. And like I said, there's actually more information. You just kind of showed a little bit of a subset of this poll. And so we're going to work on trying to get that out in a format that we can maybe put on a broader public seminar and share like more of that information, because I think it's really interesting, especially as we're seeing these trends change over time around Alaskans, how they perceive their energy prices, you know, again, like different versions or iterations of what projects and technologies they're supportive of, what their concerns are, how closely they're tracking their energy bills, how they're heating their homes, like all these different questions, right? So hopefully we'll do that as like an ACEP webinar. So I do want to encourage everyone, in addition to signing up for the nuclear working group, which I think that we will put another slide up on here, hopefully. We also would encourage you to sign up for the ACEP, Alaska Center for Energy and Power at UAF newsletter. You can just go to our website. It should be fairly easy to find. And then we get out information about these other different events that we put on and stuff like that. So, okay, let's see. Now we're getting a couple of comments, at least in here. Did the poll indicate that advanced nuclear may address heating energy needs as well as electric power needs? We did not, David, ask that question. I can tell all of you, it's been very interesting being over here in Finland, and they're actually working on these small modular reactor designs specifically and only for heating energy. They already use about 40% of their power comes from nuclear here. There's high public support for nuclear. They have the only long-term repository that's up and running anywhere in the world for spent nuclear fuel. But what they're working on right now is how to apply low temperature, small reactor designs for heating. So I will kind of throw that out there, and hopefully we'll be able to get some of the folks over here to speak at one of the working group meetings. So that's I think all we have for today. Thank you again, David. Thanks to all the speakers today. I think there was a lot of really good information. I don't know, Sarah, if we can pull up the agenda just really quickly for tomorrow again, so that we might be able to just give folks a little bit of a preview before we sign off for today. Yes, awesome. All right. So tomorrow we're gonna have a really great set of presentations from Idaho National Lab to kind of talk a little bit about, this is tag teaming on what Jeff Waxman was talking about. We'll hear a little bit about Project Pele and the other reactors designs and technologies that are moving forward there with testing. We'll hear about the Eielson Air Force project from Oklo, who's been selected as the developer for that project. Then we'll dive into the economics. We have two different presentations, one that's broader on micronuclear, and then one that's very specific to the Alaska Railbelt, both of which are through Idaho National Lab. And then we're going to do another roundtable with a few Alaskans, different set of Alaskans, kind of wrapping us up and talking about, you know, what their observations are, what their thoughts are, and what next steps for the state look like. So that is all I have today. We're actually 4 minutes early, so I don't know. I'm just got to look at the script here and see if I'm forgetting anything. Yeah, I think that we are good for today. I think I'm going to call that good. So thanks to everybody. We had, you know, at some point, I think over 160 participants, which I believe is kind of a record for this. And we will make sure to get the slides for those that agree to allow their slides to be posted and all of the recordings up within 30 days of the end of the workshop. But hopefully we can get them a little bit sooner. We'll see what the folks at Government Event Services, Sarah and her team, can do for us. All right. Thanks, everybody. We will see you tomorrow morning at 8:30 a.m. Alaska time for day 2. All right. Thank you.